Hello, and welcome back to another evening with the Calm Scientist. I hope wherever you are tonight, you've settled into that perfect spot where comfort meets curiosity, ready to let your mind wander through one of Earth's most profound stories. Tonight, we're embarking on a journey through deep time itself, exploring the 5 great mass extinctions that have shaped our planet. And I have to warn you, this topic might be far too captivating for sleep. After all, we're talking about moments when Earth itself pressed the reset button on life. Catastrophic events so dramatic they rewrote the very rules of existence. It's the kind of bedtime story that only paleontology and geology could write together. A tale of resilience, transformation, and the incredible tenacity of life itself. If you find yourself drawn into this ancient drama, please consider giving this video a gentle like and subscribe. And if you're new here, welcome to our community of curious night owls who believe that learning and relaxation can dance together in the most beautiful way. I always love hearing where you're listening from and what time it is in your corner of the world, so feel free to share that in the comments. There's something wonderfully comforting about knowing we're all connected across time zones, united by our fascination with the deep mysteries of our planet's past. Tonight, we're not here to memorize dates or species counts. Instead, we're here to let our minds drift through the vast corridors of geological time, to feel the weight and wonder of Earth's greatest transformations, and to appreciate the remarkable story of survival and renewal that has brought us to this very moment. And if you're tired of ads interrupting your sleep, you can now get our first bundle of 15 audiobooks for just $19 down in the video description. That's around 35 hours of uninterrupted knowledge exploration for just $19. So settle in, take a deep breath, and let's journey back through hundreds of millions of years to explore how our planet has repeatedly reinvented itself through catastrophe. When we think about extinction, our minds often jump to the dinosaurs, that famous moment 66 million years ago, when a space rock the size of Mount Everest slammed into what is now the Yucatan Peninsula. But that dramatic event, as significant as it was, represents just one chapter in a much larger story. Earth has experienced 5 major mass extinction events, moments so severe that they eliminated at least 75% of all species on the planet. These weren't gradual declines or slow evolutionary shifts. These were biological catastrophes that fundamentally altered the trajectory of life on Earth. Think about that for a moment. 75% of all species gone. Imagine if 3/4 of every living thing you could see, from the tiniest bacteria to the largest animals, simply vanished within a geologically brief period. It's almost impossible to comprehend the scale of such loss, yet our planet has endured this level of devastation not once, but 5 separate times. And each time, life has somehow found a way to bounce back, to diversify, to fill the empty ecological spaces with entirely new forms of existence. These mass extinctions serve as nature's great experiments in starting over. They're like cosmic reshuffling of the deck of life, moments when the dominant players are suddenly removed from the game, creating opportunities for entirely different kinds of organisms to flourish. Without these catastrophic events, our world would look fundamentally different. The mammals that eventually gave rise to us might never have had their chance to diversify if the dinosaurs hadn't been cleared from the stage. The forest we know today might never have evolved if earlier plant communities hadn't been swept away by ancient calamities. Let's begin our journey at the very dawn of complex life, roughly 445 million years ago, when our planet was a very different place. The continents were arranged in configurations that would seem alien to us today, and most life existed in the oceans. This was the Ordovician period, a time when the seas teemed with creatures that have no modern equivalents, bizarre and beautiful organisms that represent some of evolution's most creative early experiments. Picture, if you will, ancient oceans filled with trilobites, those segmented arthropods that looked like underwater pill bugs with elaborate, often spiny shells. These weren't simple creatures. Many trilobites had sophisticated compound eyes, some of the most advanced visual systems in the early animal kingdom. Swimming alongside them were nautiloid cephalopods, relatives of modern squid and octopus, but some reaching lengths of 30 feet or more, their straight conical shells cutting through the water like living submarines. The seafloor itself was covered in gardens of strange beauty. Crinoids, often called sea lilies, swayed in the ancient currents. These weren't plants at all, but animals, echinoderms related to modern starfish and sea urchins, their stems rooted to the bottom while their feathery arms filtered plankton from the water. Among them lived brachiopods, shelled creatures that might look like clams to the casual observer, but represented an entirely different evolutionary solution to the challenge of filter feeding in marine environments. This was a world without fish as we know them, without land plants or animals of any kind. The continents were bare rock and sand, swept by winds that carried no pollen, no seeds, no hint of the green revolution that was still millions of years in the future. Life was an entirely oceanic affair, and it was incredibly diverse, having spent hundreds of millions of years experimenting with different ways to make a living in the sea. But then, something went terribly wrong. The first mass extinction event, known as the Ordovician Silurian extinction, began to unfold. This catastrophe unfolded in two distinct pulses, each separated by about 1 million years, a detail that gives us important clues about what might have caused such devastation. The first pulse eliminated many species, but it was the second wave that delivered the knockout blow, ultimately claiming about 85% of all marine species. What could cause such widespread destruction in the oceans? For decades, scientists puzzled over this mystery, studying rock formations from around the world, looking for chemical signatures and fossil evidence that might reveal the killer. The answer, when it emerged, was both elegant and terrifying in its simplicity. Earth itself had become a killer, not through volcanic eruptions or asteroid impacts, but through something far more subtle and yet equally devastating: climate change driven by the growth and melting of massive ice sheets. During the late Ordovician period, the supercontinent Gondwana, which included what would eventually become South America, Africa, Antarctica, Australia and India, began to drift across the South Pole. As land masses accumulated over the polar region, ice began to form. This wasn't just a little ice age. This was glaciation on a massive scale, with ice sheets that may have been several miles thick covering vast areas of the southern continents. When ice forms on such a scale, it locks away enormous quantities of water that would otherwise be in the oceans. Sea levels dropped dramatically, perhaps by as much as 150 meters, roughly the height of a 50-story building. Imagine the effect this would have on marine ecosystems. Vast areas of the continental shelves, the shallow seas where most marine life thrived, were suddenly exposed to air. Entire ecological communities found themselves literally high and dry. But the falling sea levels were just the beginning of the crisis. As the ice sheets grew, they reflected more and more of the sun's energy back to space, cooling the planet further in a runaway refrigeration effect. The tropical seas that had harbored most of Earth's biodiversity began to cool, disrupting the delicate temperature relationships that many species depended upon. Warm water species found themselves in increasingly cold environments, while the chemical properties of seawater itself began to change. Cold water holds more dissolved gases than warm water, and as the oceans cooled, they began to absorb more carbon dioxide from the atmosphere. This changed the ocean's chemistry, making it more acidic and altering the ability of shelled creatures to build and maintain their calcium carbonate homes. For creatures like trilobites, brachiopods, and the countless other shelled organisms of the Ordovician seas, this chemical shift was like having the very foundation of their existence slowly dissolved away. The first pulse of extinction struck as these changes reached a critical threshold. Species that had thrived for millions of years suddenly found their environments becoming uninhabitable. The shallow, warm seas that had supported such incredible diversity were disappearing, replaced by deeper, colder waters that could support far fewer species. It was a catastrophic game of musical chairs, with most of the chairs being removed while the music was still playing. But then, As if the planet realized its mistake, the ice began to melt. The continental drift that had positioned Gondwana over the South Pole continued, eventually moving much of the landmass away from the polar region. The massive ice sheets began to retreat, releasing their stored water back to the oceans. Sea levels rose rapidly, flooding back across the continental shelves and re-establishing many of the shallow sea environments. You might think this would be good news for the surviving marine life, a chance for ecosystems to recover and rebuild. And indeed, some groups did begin to bounce back during this warmer period. But the rapid environmental changes weren't finished yet. The melting ice sheets released so much water that sea levels may have risen even higher than they had been before the glaciation began. This created new patterns of ocean circulation and climate, establishing conditions that were different from anything that had existed before. More critically, the warming climate appears to have triggered changes in ocean chemistry that proved even more devastating than the cooling had been. As the planet warmed and ice melted, massive amounts of nutrients that had been locked in ice were suddenly released into the oceans. This triggered enormous blooms of plankton and bacteria, which consumed vast quantities of oxygen as they lived and died. Large areas of the ocean became anoxic, essentially devoid of the oxygen that complex marine life needed to survive. This second pulse of the extinction was even more severe than the first. Species that had managed to survive the cooling and sea level changes found themselves facing suffocation in their own environment. The beautiful reef communities built by primitive corals and other organisms collapsed as oxygen levels plummeted. The diverse communities of the Ordovician seas were replaced by much simpler ecosystems, dominated by a few hardy species that could tolerate low oxygen conditions. When the dust settled, roughly 85% of marine species had vanished forever. Entire groups of organisms that had been dominant features of Ordovician seas disappeared completely. Many families of trilobites went extinct, though the group as a whole survived to continue their long evolutionary journey. The diverse communities of early corals, brachiopods and bryozoans were devastated, with only a few lineages surviving to seed the recovery that would follow. But here's what makes this story so remarkable from our perspective as we drift towards sleep. Despite the almost unimaginable scale of this catastrophe, life didn't give up. The survivors, tough and adaptable species that had managed to endure both the cooling and warming phases of the crisis, began the slow process of evolutionary recovery. They diversified into new forms, explored new ways of making a living, and gradually filled the empty ecological niches left by the extinction. This pattern of devastation, followed by recovery and innovation, would become one of the fundamental rhythms of life on Earth. Each mass extinction, terrible as it was for the species that lived through it, also created opportunities for evolutionary experimentation. The empty world left behind by each catastrophe became a laboratory for natural selection, a place where surviving lineages could evolve in new directions without competition from the established order. The Ordovician Silurian extinction set the stage for one of the most important developments in the history of life on Earth. In the aftermath of this marine catastrophe, some organisms began to explore a completely new frontier, dry land. The first simple plants began to colonize the edges of continents, followed eventually by the first animals to venture out of the water. Without the devastation of the Ordovician seas, this colonization of land might have been delayed by millions of years, or might have taken a completely different form. As we move forward through deep time toward our next great extinction event, we encounter a world that would have seemed increasingly familiar, yet still wonderfully strange. The Silurian and Devonian periods that followed the Ordovician extinction saw an explosion of innovation in both marine and terrestrial environments. The survivors of the Great Dying had made good use of their opportunities. In the recovering oceans, new forms of reef-building corals began to construct massive limestone structures, creating some of the most extensive reef systems in Earth's history. Fish, which had been minor players in Ordovician ecosystems, began to diversify rapidly. Armored jawless fish gave way to the first jawed species, and eventually to an incredible variety of forms, including some of the largest and most fearsome predators the seas had ever known. On land, the colonisation that began tentatively in the aftermath of the Ordovician extinction accelerated dramatically. Simple moss-like plants gave way to the first forests, initially composed of strange tree ferns and primitive conifers that created entirely new kinds of ecosystems. Arthropods, the group that includes insects, spiders, and their relatives, made the transition from water to land and began to diversify into forms both familiar and bizarre. Some of these early terrestrial arthropods grew to sizes that would seem monstrous today. Dragonflies with wingspans of over 2 feet soared through Devonian skies, while millipedes the length of cars crawled through the understory of the first forests. This was possible because the atmosphere of the time contained much higher levels of oxygen than today's air, allowing the simple respiratory systems of arthropods to support much larger body sizes. But perhaps, most significantly for our own story, it was during this post-extinction recovery period that the first vertebrates began to explore life on land. Fish with muscular fins began using them to prop themselves up in shallow water, gradually developing the limb structures that would eventually carry their descendants fully onto dry land. These early tetrapods, the ancestors of all land-dwelling vertebrates, including eventually ourselves, owe their opportunity to the devastation that cleared the way for new evolutionary experiments. The Devonian period, often called the Age of Fishes, saw marine ecosystems reach new levels of complexity and sophistication. Massive reef systems built by corals and other organisms created underwater landscapes of incredible beauty and diversity. Armoured fish called placoderms evolved into some of the ocean's top predators, including Dunkleosteus, a monster over 30 feet long with bone shears instead of teeth that could bite through almost anything in the ancient seas. Yet even as these communities flourished and diversified, the seeds of the next great catastrophe were already being sown. The very success of life during the Devonian would contribute to the conditions that led to the second major mass extinction event, a reminder that in Earth's history, success and catastrophe often walk hand in hand. The late Devonian extinction, which occurred roughly 375 million years ago, was a more gradual affair than the sudden catastrophe that ended the Ordovician. This extinction unfolded over several million years, coming in a series of pulses that systematically dismantled the complex ecosystems that had flourished during the Devonian recovery. By the time it was over, about 75% of species had vanished, with marine ecosystems bearing the brunt of the devastation. What makes the late Devonian extinction particularly fascinating is that it appears to have been caused, at least in part, by life itself. The great forests that had colonized the continents during the Devonian were incredibly successful, spreading across vast areas and fundamentally changing how the planet's surface interacted with the atmosphere. These early forests were composed largely of tree ferns, primitive conifers, and other plants that had evolved elaborate root systems to anchor themselves in soil. But here's where the story takes an ironic turn. These root systems were incredibly effective at breaking down rock through both physical and chemical weathering. As the forest spread, they accelerated the rate at which continental rock was worn away and carried to the sea. This sounds like it might be beneficial, providing nutrients for marine ecosystems, but like many things in Earth's complex systems, the reality was more complicated. The massive influx of nutrients from terrestrial weathering triggered enormous blooms of plankton and bacteria in the oceans. These microscopic organisms consumed vast quantities of nutrients and oxygen, and when they died, their decomposition further depleted oxygen levels. Large areas of the ocean became anoxic, creating dead zones where complex marine life simply could not survive. At the same time, the burial of all this organic matter from plankton blooms began to draw down carbon dioxide levels in the atmosphere. While this might sound environmentally beneficial from our modern perspective, in the context of the late Devonian, it contributed to global cooling that further stressed marine ecosystems adapted to warmer conditions. The combination of ocean anoxia and climate cooling created a 1-2 punch that devastated marine life. The elaborate reef systems that had been such a feature of Middle Devonian seas collapsed as corals and other reef-building organisms succumbed to oxygen depletion and temperature changes. Many groups of fish, including most of the giant armoured placoderms that had ruled Devonian seas, disappeared forever. On land, the effects were less severe but still significant. Many early forest ecosystems were disrupted, and several groups of early tetrapods went extinct. However, some lineages of land-dwelling vertebrates survived and even thrived in the changing conditions, setting the stage for the great diversification of terrestrial vertebrates that would characterize the following Carboniferous period. The late Devonian extinction reminds us that Earth's systems are interconnected in ways that are often surprising and sometimes counterintuitive. The success of early forests in colonizing land had consequences that rippled through the entire planet, ultimately contributing to a mass extinction event that reshaped marine ecosystems. It's a powerful reminder that in Earth's complex web of interactions, actions in one sphere can have unexpected and far-reaching consequences in completely different environments. As we drift through these ancient catastrophes, there's something almost dreamlike about the scale and strangeness of it all. We're talking about events so removed from human experience, so vast in their scope and consequences, that they take on an almost mythological quality. Yet these aren't myths or fantasies, these are real events, documented in rock layers around the world, that fundamentally shaped the trajectory of life on our planet. Take a moment to consider the deep time perspective we're exploring tonight. 375 million years ago, when the late Devonian extinction was unfolding, is almost incomprehensibly ancient from our human perspective. If you could travel back to that time, you would find yourself on a planet that was recognizably Earth, with familiar physics and chemistry, but inhabited by creatures so alien that they might as well have come from another world entirely. The recovery from the late Devonian extinction set the stage for one of the most remarkable periods in Earth's history, the Carboniferous period. This was the time when terrestrial ecosystems really came into their own, when the first great forests spread across the continents and began to fundamentally alter the planet's atmosphere and climate. It was also the time when vertebrate life on land began its great diversification, splitting into the lineages that would eventually give rise to all modern groups of terrestrial vertebrates. The Carboniferous forests were unlike anything that exists today. They were dominated by giant tree ferns, some reaching heights of over 100 feet, and by primitive relatives of modern club mosses that grew to the size of large trees. These weren't the flowering plants that dominate modern forests, they were ancient lineages that had evolved their own solutions to the challenges of life on land, creating ecosystems with a distinctly alien character. These forests grew in warm, humid conditions across much of the globe, and they were incredibly productive. They locked away vast quantities of carbon in their tissues, and when they died, much of this organic matter was buried in swamps and eventually transformed into the coal deposits that would later power human civilization. In fact, so much carbon was removed from the atmosphere during the Carboniferous that oxygen levels rose to unprecedented heights, reaching concentrations of 35% or more compared to today's 21%. This oxygen-rich atmosphere had profound consequences for terrestrial life. Arthropods, whose simple respiratory systems are limited by oxygen availability, grew to enormous sizes. Dragonflies with wingspans over 2.5 feet patrolled Carboniferous skies. Millipedes reached lengths of 6 feet or more. Even more dramatically, some arachnids grew to truly monstrous proportions, with sea scorpions in coastal waters reaching lengths of 8 feet or more. But it was during this period of high oxygen and lush forests that vertebrate life on land really began to diversify. Early tetrapods split into two major lineages that persist to this day. One group gave rise to modern amphibians, while the other evolved into reptiles, and eventually into all other terrestrial vertebrates, including dinosaurs, birds, and mammals. Some of these early terrestrial vertebrates grew to impressive sizes, taking advantage of the abundant plant life and high oxygen levels. Amphibians the size of crocodiles lurked in Carboniferous swamps, while the first large reptiles began to explore new ways of making a living on land. It was a time of evolutionary experimentation, as vertebrates explored the possibilities of life in terrestrial environments. Yet even as these rich ecosystems flourished, the conditions that supported them were slowly changing. The high productivity of carboniferous forests was gradually drawing down atmospheric carbon dioxide levels, and the climate was beginning to cool. Ice was starting to form at the poles once again, setting the stage for another round of environmental upheaval. The transition from the Carboniferous to the Permian period, which began about 299 million years ago, saw dramatic changes in both climate and ecosystems. The lush, swampy forests of the Carboniferous gave way to more arid conditions as the climate cooled and dried. Many of the giant tree ferns and club moss forests disappeared, replaced by the first conifers and other drought-tolerant plants. These environmental changes put pressure on terrestrial ecosystems, but they also created new opportunities. Reptiles, with their waterproof skin and efficient kidneys, were better adapted to dry conditions than amphibians, and they began to diversify rapidly. Some evolved into herbivores that could take advantage of the new plant communities, while others became predators that hunted these plant eaters. During the Permian, vertebrate life on land reached new levels of complexity and sophistication. Some reptiles evolved into forms that prefigured later dinosaurs, while others developed along completely different evolutionary paths. The synapsids, the group that includes modern mammals and their extinct relatives, became particularly diverse and successful during this period. Some synapsids evolved into massive herbivores, like the sail-backed Dilophosaurus, while others became fearsome predators, like the saber-toothed Enostrancevia. These weren't mammals as we know them, but they were our ancestors, early members of the lineage that would eventually give rise to all modern mammals, including ourselves. Marine ecosystems during the Permian were also reaching new heights of complexity. Reefs built by a variety of organisms, including primitive corals, sponges and other creatures, created underwater landscapes of incredible diversity. The seas teemed with a wide variety of fish, marine reptiles and invertebrates. It was, by many measures, the most biodiverse period in Earth's history, a time when life had recovered from the earlier extinction events and was exploring an incredible range of evolutionary possibilities. But this golden age of biodiversity was about to come to a catastrophic end. The third mass extinction event, the one that marks the boundary between the Permian and Triassic periods about 252 million years ago, was the most severe crisis that life on Earth has ever faced. It's sometimes called the Great Dying, and that name captures something essential about the scale of devastation involved. When this extinction was over, an estimated 96% of marine species and 70% of terrestrial vertebrate species had vanished. It was the closest that life on Earth has ever come to complete annihilation, a catastrophe so severe that it took millions of years for ecosystems to recover even basic levels of complexity. To understand what could cause such devastating losses, we need to look at one of the most dramatic geological events in our planet's history. The story of the Great Dying begins with volcanism on a scale that dwarfs anything in recorded human history. In what is now Siberia, massive volcanic eruptions began that would continue for hundreds of thousands of years, creating the Siberian Traps, one of the largest volcanic features on Earth. These weren't ordinary volcanic eruptions. This was flood basalt volcanism, where enormous volumes of lava poured out of long fissures in the ground, covering vast areas with molten rock. The scale of these eruptions is almost impossible to comprehend. The Siberian Traps cover an area roughly the size of the continental United States, and in some places the volcanic rock is over 2 miles thick. The volume of lava involved is estimated at around 1 million cubic miles, enough to bury the entire continental United States under a layer of rock nearly half a mile deep. But it wasn't just the lava that made these eruptions so devastating. The volcanism released enormous quantities of toxic gases into the atmosphere, including sulfur dioxide, carbon dioxide, and various other compounds that had profound effects on global climate and atmospheric chemistry. the sulfur dioxide formed acid rain that fell across much of the planet, while the carbon dioxide triggered rapid global warming through the greenhouse effect. The environmental changes triggered by the Siberian volcanism were both rapid and extreme. Global temperatures rose by as much as 8 to 10 degrees Celsius, turning much of the planet into a hot, hostile environment. The oceans became acidic and depleted of oxygen, creating conditions that were toxic to most marine life. On land, acid rain and extreme temperatures made survival difficult for most organisms. But the volcanism may have triggered even more devastating feedback effects. As the planet warmed, vast deposits of frozen methane in ocean sediments and permafrost began to decompose, releasing additional greenhouse gases that accelerated the warming trend. This created a runaway greenhouse effect that pushed global temperatures even higher and made recovery even more difficult. The Great Dying unfolded over several 100,000 years, coming in multiple pulses that systematically dismantled Earth's ecosystems. Each pulse eliminated more species and made conditions even more difficult for survivors. By the time the crisis was over, the planet's biosphere had been reduced to a fraction of its former complexity and diversity. The aftermath of the Great Dying was a world that would have seemed almost lifeless compared to the rich ecosystems that had preceded it. The complex reef systems of the Permian seas had collapsed completely, leaving behind simple communities dominated by a few hardy species. On land, the diverse vertebrate faunas of the late Permian were reduced to a handful of surviving lineages, mostly small, generalized species that could tolerate the harsh conditions. Yet even in this devastated world, life found a way to persist and eventually recover. The survivors of the Great Dying, though few in number and limited in diversity, carried within their genes the potential for all the evolutionary innovations that would follow. They were the ancestors of dinosaurs, mammals, birds, and all the other groups that would eventually repopulate the planet. The recovery from the Great Dying was slow, taking millions of years to restore even basic ecosystem complexity. But when recovery did come, it ushered in entirely new kinds of ecosystems and evolutionary innovations. The Triassic period that followed the extinction saw the rise of the first dinosaurs, the first mammals, and the first flowering plants, setting the stage for the modern world. The early Triassic was a time of tentative recovery, when the few surviving lineages began the slow process of evolutionary diversification. In the devastated oceans, simple communities gradually gave way to more complex ecosystems. New types of marine reptiles appeared, including the first ichthyosaurs, dolphin-like creatures that had evolved from land-dwelling reptiles and returned to the sea. These early marine reptiles were small and relatively simple compared to the giants that would follow, but they represented an important step in the recovery of marine ecosystems. On land, the surviving archosaurs, the group that includes crocodiles, dinosaurs, and birds, began to diversify into new ecological roles. Some became large predators, while others evolved into herbivores that could take advantage of the slowly recovering plant communities. The first true dinosaurs appeared during the Middle Triassic, initially as small bipedal predators that were just one component of much more diverse reptilian communities. But the Triassic recovery was interrupted by yet another mass extinction event, the fourth in our series of planetary catastrophes, the Triassic-Jurassic extinction, which occurred about 201 million years ago, eliminated roughly 80% of species and fundamentally reshaped terrestrial ecosystems. This extinction was smaller in scale than the Great Dying, but it had profound consequences for the future of life on Earth. Like the Great Dying before it, the Triassic-Jurassic extinction appears to have been triggered by massive volcanism. This time, the culprit was the breakup of the supercontinent Pangaea, which had formed during the Permian and was now beginning to split apart. As North America separated from Africa and South America, enormous volcanic eruptions occurred along the spreading rift zones. These eruptions, known as the Central Atlantic Magmatic Province, were similar in scale to the Siberian traps, though somewhat smaller. They released vast quantities of carbon dioxide and other gases into the atmosphere, triggering rapid climate change and ocean acidification. The environmental disruption was severe enough to eliminate many of the groups that had survived the Great Dying and were finally beginning to recover. The Triassic-Jurassic extinction had a particularly dramatic effect on terrestrial vertebrate communities. Many of the large archosaurs that had dominated late Triassic ecosystems disappeared, along with the last of the large synapsids that had been such important components of Permian and Triassic faunas. The extinction cleared the way for dinosaurs, which had been relatively minor players in Triassic ecosystems, to become the dominant large animals on land. This is one of the most striking examples of how mass extinctions can redirect the course of evolutionary history. Without the Triassic-Jurassic extinction, dinosaurs might have remained small, specialized predators living in the shadow of other reptilian groups. Instead, the extinction eliminated their competitors and opened up ecological opportunities that dinosaurs quickly exploited. The Jurassic period that followed the extinction saw dinosaurs diversify into an incredible array of forms. Long-necked sauropods evolved into some of the largest land animals that have ever lived, while predatory theropods developed into increasingly sophisticated hunters. Armored dinosaurs, horned dinosaurs, and duck-billed dinosaurs would all trace their lineages back to the evolutionary radiation that followed the Triassic-Jurassic extinction. In the oceans, marine ecosystems also underwent dramatic changes. New groups of marine reptiles appeared, including the massive plesiosaurs and the streamlined ichthyosaurs, which grew to enormous sizes and became the ocean's top predators. Ammonites, relatives of modern squid and octopus with elaborate coiled shells, diversified into hundreds of species and became some of the most abundant and successful marine animals. The Jurassic was also the time when flowering plants first appeared, though they remained relatively uncommon compared to the conifers, ferns, and cycads that dominated most terrestrial plant communities. These early flowering plants were small and simple compared to modern varieties, but they represented a revolutionary innovation that would eventually transform terrestrial ecosystems. But perhaps, most significantly for our own story, it was during the Jurassic that the first mammals began to diversify, though they remained small and relatively inconspicuous in dinosaur-dominated ecosystems. These early mammals were mostly tiny, shrew-like creatures that lived in the shadows of the great reptiles, but they possessed several key innovations that would prove crucial for their eventual success. Early mammals had evolved sophisticated temperature regulation, allowing them to remain active in cool conditions that slowed down their cold-blooded competitors. They had also developed complex teeth that allowed them to process a wide variety of foods, and their reproductive strategies, including live birth and milk production, gave their offspring significant advantages in survival. The Jurassic period established many of the patterns that would characterize the Mesozoic era, often called the Age of Reptiles. Dinosaurs dominated terrestrial ecosystems, marine reptiles ruled the oceans, and the first birds took to the skies. It was a time of relative stability and gradual evolutionary change, when ecosystems had recovered from the devastation of earlier extinctions and were exploring new levels of complexity and sophistication. The Cretaceous period that followed the Jurassic saw these trends continue and accelerate. Dinosaurs reached their peak diversity during the Cretaceous, evolving into forms that still capture our imagination today. Massive predators like Tyrannosaurus rex stalked herds of equally impressive herbivores like Triceratops and Edmontosaurus. In the skies, pterosaurs grew to enormous sizes, with some species having wingspans approaching 40 feet. The Cretaceous was also when flowering plants finally came into their own, diversifying rapidly and beginning to dominate many terrestrial plant communities. This flowering plant revolution had cascading effects throughout terrestrial ecosystems, providing new food sources that supported the evolution of new groups of insects, which in turn provided food for other animals. The complex web of interactions between flowering plants, pollinating insects, and other organisms that characterizes modern terrestrial ecosystems first emerged during the Cretaceous. In the oceans, Cretaceous marine ecosystems reached levels of complexity and diversity that rivaled or exceeded anything that had come before. massive marine reptiles like Mosasaurus, relatives of modern monitor lizards that had returned to the sea, competed with enormous sharks and other predators for dominance in ancient seas. Ammonites reached their peak diversity, evolving into hundreds of species with shells of incredible variety and beauty. Yet beneath this apparent stability and success, changes were occurring that would set the stage for the most famous mass extinction event in Earth's history. Volcanic activity was increasing in many parts of the world, and sea levels were rising to heights not seen for millions of years. Climate was warm and relatively stable, but there were hints of instability that suggested the Cretaceous world might not be as secure as it appeared. The end came suddenly and dramatically 66 million years ago, in the form of an asteroid impact that ranks among the most catastrophic events in Earth's history. The Cretaceous Paleogene extinction, the fifth and most recent of the great mass extinctions, eliminated roughly 75% of species and brought the age of reptiles to an abrupt and violent end. The story of this extinction begins in space, with an asteroid roughly 6 to 10 miles in diameter that had been orbiting the Sun for billions of years. This chunk of rock and metal about the size of Mount Everest was following a trajectory that would eventually bring it into collision with our planet. When that collision occurred, the energy released was equivalent to billions of nuclear weapons detonating simultaneously. The asteroid struck what is now the Yucatan Peninsula of Mexico, creating the Chicxulub crater, a structure over 100 miles in diameter that represents one of the most dramatic scars on our planet's surface. The impact instantly vaporized the asteroid and enormous quantities of rock, creating a fireball that reached temperatures of thousands of degrees and ejected material high into the atmosphere and even into space. The immediate effects of the impact were catastrophic beyond imagination. Shock waves from the collision triggered massive earthquakes around the globe, while the impact itself generated tsunamis hundreds of feet high that swept across ocean basins. The ejected material, heated to incandescence by the violence of the impact, rained back down on the planet like a global firestorm, igniting wildfires across entire continents. But it was the longer-term environmental effects that proved most devastating to life on Earth. The impact ejected so much dust and debris into the atmosphere that sunlight was blocked for months or possibly years. This impact winter brought photosynthesis to a virtual halt, collapsing food chains from the bottom up. Plants died first, followed by herbivores, and finally by the predators that depended on them. The darkness was followed by other environmental stresses. Acid rain, formed when impact debris reacted with atmospheric moisture, fell across much of the planet. The massive wildfires released enormous quantities of carbon dioxide and other gases, triggering climate changes that persisted long after the initial impact effects had faded. Ocean chemistry changed dramatically, becoming more acidic and depleted of oxygen. Large animals were hit particularly hard by these environmental changes. Dinosaurs, which had dominated terrestrial ecosystems for over 150 million years, found themselves unable to cope with the sudden environmental collapse. Within a few 100,000 years, all non-avian dinosaurs had vanished from the fossil record, ending one of the most successful chapters in the history of life on Earth. The extinction wasn't limited to dinosaurs. Marine reptiles like mosasaurs and plesiosaurs disappeared completely. Ammonites, which had survived multiple earlier mass extinctions, finally succumbed to this latest catastrophe. Pterosaurs, the first vertebrates to achieve powered flight, vanished from the skies. Even many groups of marine plankton, the foundation of ocean food webs, suffered massive losses. Yet not everything died. Birds, which are actually a group of dinosaurs that had evolved flight, managed to survive the extinction, though most lineages were eliminated. Mammals, still small and relatively insignificant during the late Cretaceous, proved remarkably resilient to the environmental changes. Crocodiles, turtles, and many other reptilian groups also survived, along with most amphibians and fish. The pattern of survival reveals important clues about what determined which groups made it through the crisis. Small size was clearly advantageous, as was the ability to survive on limited food resources. Animals that could hibernate or enter torpor, or that had flexible diets, were more likely to survive than large, specialized species. The survivors were, in many cases, the ecological generalists, the species that were tough, adaptable, and not too dependent on any particular environment or food source. The aftermath of the Cretaceous-Paleogene extinction was a world transformed. The dominant large animals of the Mesozoic were gone, replaced by much smaller, more generalized species. Early Paleocene ecosystems were dominated by small mammals, most no larger than modern house cats, that began to explore the ecological opportunities left vacant by the extinction of dinosaurs. This post-extinction world was, in many ways, a laboratory for mammalian evolution. Without competition from dinosaurs, mammals began to diversify rapidly into ecological roles that had been occupied by reptiles for over 150 million years. Some evolved into large herbivores, others became predators, and still others developed specialized lifestyles that had no precedent in mammalian history. The evolutionary radiation that followed the Cretaceous-Paleogene extinction gave rise to most of the major groups of mammals that exist today. Primates, the group that includes humans, first appeared during this period, as did the ancestors of elephants, whales, bats, and countless other mammalian lineages. It was this post-extinction diversification that set the stage for the mammal-dominated world we know today. In the oceans, the extinction of marine reptiles opened up opportunities for other groups to expand into new ecological roles. Early whales, evolved from land-dwelling mammals, began their return to the sea during the Paleocene and Eocene epochs. Sharks and bony fish diversified into forms that would become familiar components of modern marine ecosystems. The recovery of terrestrial plant communities was equally dramatic. The extinction had eliminated many Cretaceous plant species, but the survivors quickly began to diversify and spread. Flowering plants, which had been important but not dominant during the Cretaceous, became the primary components of most terrestrial ecosystems. Grasses, which had appeared late in the Cretaceous, began their remarkable expansion that would eventually lead to the grassland ecosystems that cover much of the world today. This brings us to a profound realization as we consider these 5 great mass extinctions from our comfortable perspective millions of years later. Each of these catastrophic events, terrible as they were for the species that lived through them, played a crucial role in shaping the evolutionary history that led to our own existence. Without the Ordovician extinction, the colonization of land might have been delayed. Without the Permian extinction, dinosaurs and mammals might never have evolved. Without the Cretaceous extinction, mammals might have remained small, nocturnal creatures living in the shadow of reptilian giants. This doesn't mean that mass extinctions are good things, of course. Each represented an almost unimaginable loss of evolutionary history, the elimination of countless species that represented millions of years of evolutionary innovation. The beautiful trilobites of the Paleozoic, the massive dinosaurs of the Mesozoic, the bizarre marine reptiles of the Cretaceous, all represent evolutionary experiments that can never be repeated. Their loss diminished the richness and complexity of life on Earth in ways that can never be fully measured or understood. Yet the story of mass extinctions is also a story of resilience, of life's remarkable ability to recover from even the most devastating setbacks. After each extinction, the survivors found ways to rebuild, to diversify, to explore new evolutionary possibilities. The history of life on Earth is not just a story of loss and devastation, but also of recovery, innovation, and renewal. Consider the deep time perspective we've been exploring tonight. These 5 mass extinction events span roughly 400 million years, a period so vast that it encompasses the entire history of complex life on land. During this time, continents have drifted across the globe, climates have shifted from ice ages to greenhouse conditions and back again, and life has experimented with an almost infinite variety of forms and lifestyles. From our human perspective, 400 million years is almost incomprehensibly long. Our entire species has existed for only the last few 100,000 years, a blink of an eye in geological terms, All of recorded human history represents less than 1/100th of 1% of the time period we've been discussing tonight. Yet this vast span of deep time is preserved in the rocks beneath our feet, in fossil specimens housed in museums around the world, and in the genetic legacy carried by every living organism. Each mass extinction event left its signature in the geological record, creating distinct boundaries that geologists use to divide Earth's history into different periods and eras. The rocks tell the story of these ancient catastrophes through changes in fossil assemblages, through chemical signatures of environmental upheaval, and through the physical evidence of the events themselves, like the shocked quartz and iridium anomalies that mark the Cretaceous-Paleogene boundary. But perhaps most remarkably, these ancient events are also recorded in the very structure of modern ecosystems. The fact that mammals dominate terrestrial environments today is a direct consequence of the Cretaceous extinction that eliminated dinosaurs. The diversity of flowering plants that surrounds us is partly a legacy of the evolutionary radiations that followed earlier extinctions. Even our own existence as a species can be traced back through a lineage that survived each of these 5 great catastrophes. This raises profound questions about the nature of evolutionary history and the role of contingency in shaping the world we know. If any of these mass extinctions had not occurred or had unfolded differently, the entire trajectory of evolution on Earth might have taken a completely different path. We might be living in a world still dominated by dinosaurs, or marine reptiles, or some group of organisms that never got their evolutionary chance because they were eliminated by an ancient catastrophe. The study of mass extinctions also provides important insights into the workings of Earth's environmental systems and the ways in which life and environment interact over geological timescales. Each extinction event was triggered by different causes, from volcanism to asteroid impacts to climate change. But they all shared certain common features. They all involved rapid environmental changes that exceeded the ability of many species to adapt. They all disrupted food webs and ecological relationships in ways that cascaded through entire ecosystems. And they all demonstrated the interconnected nature of Earth's systems, showing how changes in one part of the planet can have consequences that reach around the globe. These lessons from deep time have important implications for understanding modern environmental challenges. While the current rate of species extinction doesn't yet approach the levels seen during the great mass extinctions of the past, many scientists argue that we are in the early stages of a 6th mass extinction, one caused not by volcanism or asteroid impacts, but by human activities. The patterns observed in ancient extinction events provide insights into how modern ecosystems might respond to ongoing environmental changes. But tonight, as we drift through these ancient catastrophes from the comfort of our modern world, perhaps the most important message is one of wonder and perspective. The fact that we exist at all is a testament to the resilience of life and the power of evolutionary processes to create complexity and beauty, even in the face of almost unimaginable destruction. We are the inheritors of 4 billion years of evolutionary history, the products of countless generations of organisms that somehow managed to survive whatever catastrophes our planet could throw at them. Every breath we take connects us to the ancient atmosphere that those early survivors breathed. Every heartbeat echoes the cardiovascular innovations that allowed our ancestors to survive environmental upheavals that eliminated most of their contemporaries. The very structure of our cells carries molecular machinery that has been refined through billions of years of evolution, including passage through each of the 5 great mass extinction events. As we continue our journey through deep time, it's worth reflecting on the incredible improbability of our own existence. If you could travel back to any point during the first 4 billion years of Earth's history and examine the biosphere of that time, it would be essentially impossible to predict that evolution would eventually produce creatures capable of contemplating their own evolutionary history. The path from simple cells to complex multicellular organisms to intelligent beings capable of scientific thought involved countless contingent events, any one of which could have derailed the entire process. Yet here we are, products of this impossible journey, able to read the story of our own origins in the rocks and fossils that surround us. We can trace our lineage back through each mass extinction, identifying the specific ancestors that managed to survive when most of their contemporaries perished. We can understand the environmental changes that shaped our evolutionary history and appreciate the remarkable series of events that led to our own existence. This deep time perspective provides a profound sense of connection to the natural world and to the long history of life on Earth. We are not separate from nature, but rather the current expression of natural processes that have been operating for billions of years. The elements that make up our bodies were forged in ancient stars and have been recycled through countless organisms over geological time. The genetic code that guides our development is a direct inheritance from the earliest life forms, modified and refined through eons of evolution, but still recognizably connected to its ancient origins. The mass extinctions we've explored tonight represent some of the most dramatic chapters in this long story, moments when the normal course of evolution was interrupted by catastrophic events that reset the trajectory of life on Earth. Yet even these catastrophes were part of the natural order, expressions of the dynamic processes that have always characterized our planet. Earth is not a static, unchanging world, but rather a dynamic system where change is the only constant and where life must constantly adapt to new challenges and opportunities. Understanding this dynamic nature of Earth's systems helps us appreciate both the fragility and the resilience of life. Species and ecosystems can be incredibly vulnerable to rapid environmental changes, as demonstrated by the massive losses during each extinction event. Yet life as a whole has proven remarkably resilient, able to recover from even the most devastating setbacks and to evolve new forms of complexity and beauty. This resilience doesn't come from any single species or ecosystem, but rather from the diversity of life itself. The survivors of each mass extinction were typically not the most dominant or successful species of their time, but rather the most adaptable and generalized forms. Diversity provides insurance against catastrophe, ensuring that some lineages will possess the characteristics needed to survive whatever challenges the future might bring. As we near the end of our journey through these ancient catastrophes, it's worth considering what lessons they might hold for our own time. While the specific causes of modern environmental changes are different from those that triggered ancient mass extinctions, the underlying principles remain the same. Rapid environmental change can disrupt ecosystems in ways that cascade through entire biological communities. Species that are highly specialized or restricted to particular environments are more vulnerable than those that are adaptable and widespread. And the interconnected nature of Earth's systems means that changes in one area can have far-reaching consequences in completely different parts of the world. But perhaps the most important lesson from the deep time perspective is one of humility and wonder. The history of life on Earth is far longer and more complex than human history, and it will continue long after our own species has passed into the fossil record. We are temporary participants in an ongoing story that began billions of years ago and will continue for billions of years into the future. Understanding our place in this vast narrative can provide both perspective on our current challenges and appreciation for the remarkable journey that led to our existence. The 5 mass extinction events we've explored tonight are just the most dramatic episodes in this ongoing story. Between them lie millions of years of gradual evolutionary change, of species appearing and disappearing, of ecosystems assembling and dissolving, of life constantly exploring new possibilities and adapting to changing conditions. Each day brings thousands of small evolutionary changes as organisms respond to environmental pressures and opportunities. The grand drama of life continues to unfold even as we sleep, in ways both subtle and profound. Now, let's shift our perspective from the broad sweep of these catastrophic events to examine the intricate mechanisms that drive extinction and recovery. Understanding how ecosystems collapse and rebuild reveals patterns that transcend any single extinction event, illuminating fundamental principles about how life responds to crisis. When we examine the anatomy of extinction, we discover that ecosystems don't simply vanish overnight. even during the most catastrophic events. Instead, they unravel in predictable ways, following patterns that ecologists have come to recognize across different time periods and different types of environmental stress. The process typically begins with the most specialized species, those that have evolved to exploit very specific resources or environmental conditions. Consider the intricate relationships that exist in any healthy ecosystem. Flowering plants depend on specific pollinators, predators rely on particular prey species, and countless organisms have evolved to occupy narrow ecological niches. These specialized relationships represent millions of years of coevolution, but they also create vulnerabilities. When environmental conditions change rapidly, the most finely tuned relationships are the first to break down. During the Cretaceous-Paleogene extinction, for example, the elaborate relationships between flowering plants and their pollinators were severely disrupted. Many plant species that had co-evolved with specific insects found themselves without their partners, leading to cascading effects throughout terrestrial ecosystems. The loss of these primary relationships then rippled upward through food webs, affecting herbivores that depended on those plants and predators that hunted those herbivores. This cascading pattern of ecosystem collapse reveals why mass extinctions are so devastating. It's not just that individual species die out, but that the complex web of relationships that bind ecosystems together begins to unravel. Each broken link makes the entire system more fragile, more susceptible to further disruption. Eventually, what began as environmental stress on a few species becomes a system-wide collapse that can eliminate entire biological communities. Yet, within this process of collapse lie the seeds of recovery. The species that survive mass extinctions typically share certain characteristics that make them resilient to environmental upheaval. They tend to be generalists rather than specialists, able to survive on a variety of food sources and tolerate a range of environmental conditions. They're often relatively small, requiring fewer resources and able to maintain viable populations even when resources are scarce. The mammals that survived the Cretaceous extinction exemplify these survival characteristics. Most were small, nocturnal creatures with flexible diets and the ability to regulate their body temperature. These traits, which had evolved for entirely different reasons during the Mesozoic, proved crucial for surviving the environmental catastrophe that eliminated the dinosaurs. Their small size meant they needed less food during the impact winter. Their nocturnal habits helped them avoid the worst effects of the global firestorm, and their warm-blooded physiology allowed them to remain active even as temperatures fluctuated wildly. But survival is only the first step in the post-extinction story. What happens next, during the recovery phase, is equally fascinating and reveals profound truths about the creative power of evolution. In the empty world left behind by mass extinction, the survivors find themselves in a landscape of opportunity. Ecological niches that had been occupied for millions of years are suddenly vacant, and natural selection begins the process of filling them with new forms of life. This process, known as adaptive radiation, can proceed with remarkable speed. Within just a few million years after the Cretaceous extinction, mammals had diversified from small, generalized forms into species as different as early primates, primitive ungulates, and the ancestors of modern carnivores. Each group was exploring different ways of making a living in the post-extinction world, experimenting with new body plans, new feeding strategies, and new ecological relationships. The speed of this diversification reveals something important about evolutionary potential. During normal times, when ecosystems are stable and ecological niches are already occupied, evolution tends to proceed relatively slowly. Existing species have already adapted to available opportunities, and there's limited room for dramatic innovation. But mass extinctions reset this evolutionary game, creating what paleontologists call ecological release. In the aftermath of extinction, surviving lineages suddenly find themselves free from the competitive constraints that had previously limited their evolutionary options. They can evolve into larger body sizes, explore new feeding strategies, and colonize environments that had previously been unavailable to them. The result is often an explosion of evolutionary experimentation as different lineages try out various solutions to the challenges of life in the post-extinction world. This pattern of post-extinction diversification has occurred after each of the 5 great mass extinctions, but it's particularly well documented in the fossil record following the Permian and Cretaceous events. After the Great Dying, the archosaurs that gave rise to dinosaurs, crocodiles, and pterosaurs underwent rapid diversification. After the Cretaceous extinction, mammals experienced their own evolutionary explosion, rapidly expanding into ecological roles that had been occupied by dinosaurs for over 150 million years. But adaptive radiation doesn't occur in isolation. As new species evolve and ecosystems begin to rebuild, complex interactions develop between the recovering biota and Earth's physical systems. The spread of grasses after the Cretaceous extinction, for example, didn't just represent the success of a new plant group. Grasslands create new soil types, change patterns of erosion and sedimentation, and even influence regional climate patterns through their effects on water cycles and albedo. These feedbacks between life and environment reveal another crucial aspect of extinction and recovery. The process is not simply biological, but represents a complex interplay between living systems and the physical Earth. During mass extinctions, disruptions to biological systems can trigger changes in atmospheric chemistry, ocean circulation, and even geological processes. During recovery, the evolution of new life forms can, in turn, modify environmental conditions in ways that influence further evolutionary change. The rise of land plants after the Ordovician extinction provides a striking example of this life-environment feedback. As plants colonized terrestrial environments, they began to alter soil formation, atmospheric composition, and hydrological cycles. These changes created new environmental conditions that influenced the further evolution of both plants and the animals that eventually joined them on land. The colonization of land wasn't just an evolutionary achievement, it was a transformation of Earth's surface that created entirely new types of environments. Similarly, the evolution of photosynthesis billions of years earlier had transformed Earth's atmosphere by adding oxygen, creating the conditions that made complex multicellular life possible. The Great Oxidation event, which occurred around 2.5 billion years ago, was itself a form of mass extinction, eliminating many organisms that couldn't tolerate the newly oxygenated environment. Yet it also set the stage for all subsequent evolution of complex life. These deep connections between biological and physical systems help explain why Earth's history shows such a strong pattern of punctuated change. Long periods of relative stability are interrupted by episodes of rapid transformation, when biological and environmental changes reinforce each other in positive feedback loops. Mass extinctions represent the most dramatic examples of these transformative episodes, but similar patterns occur at smaller scales throughout Earth's history. Understanding these patterns provides insights into the nature of complex systems and the ways in which they respond to perturbation. Earth's biosphere is what scientists call a complex adaptive system, characterized by multiple interacting components, emergent properties, and non-linear responses to change. In such systems, small changes can sometimes have large effects, while large perturbations don't always produce proportional responses. The Permian extinction illustrates this non-linear behavior perfectly. The initial volcanic eruptions in Siberia were certainly massive, but they might not have caused such devastating extinction if they hadn't triggered feedback effects that amplified the environmental disruption. The release of methane from warming ocean sediments, the collapse of marine productivity, and the acidification of seawater all represented positive feedbacks that made the crisis far worse than the initial volcanism alone could have caused. Conversely, life's recovery from mass extinctions demonstrates the remarkable resilience that can emerge from complex adaptive systems. Even when most species are eliminated, the surviving remnants contain enough genetic and ecological diversity to seed the eventual restoration of ecosystem complexity. The information stored in DNA, the basic metabolic pathways that power cellular life, and the fundamental ecological relationships between producers and consumers all persist through even the most severe extinctions. This resilience doesn't mean that recovery is inevitable or that all lost diversity can be restored. Each mass extinction permanently eliminates unique evolutionary experiments that can never be repeated. The specific adaptations that allowed trilobites to thrive in Paleozoic seas, or that enabled dinosaurs to dominate Mesozoic landscapes, represent irreplaceable losses to the history of life. Recovery creates new forms of complexity and diversity, but not necessarily the same forms that existed before. The implications of this perspective extend far beyond paleontology and geology. The study of mass extinctions provides insights into how any complex system responds to crisis and change. These insights are relevant to understanding everything from ecosystem management to social and economic systems. The patterns revealed by Earth's history suggest that resilience in complex systems comes not from rigid stability, but from diversity, flexibility, and the capacity for rapid adaptation when circumstances change. Modern conservation biology has drawn heavily on lessons from paleontology in developing strategies for protecting biodiversity in the face of ongoing environmental change. The recognition that small, isolated populations are more vulnerable to extinction has led to efforts to maintain connectivity between protected areas. The understanding that generalist species are often more resilient than specialists has influenced decisions about which species to prioritize for conservation efforts. But perhaps the most important insight from the deep time perspective is the recognition that change, even catastrophic change, is a fundamental feature of Earth's systems. The planet we inhabit today is the product of billions of years of environmental upheaval and biological response. The stability we experience in our brief human lifetimes is actually quite unusual from a geological perspective. Understanding this can help us develop more realistic expectations about environmental change and more effective strategies for adapting to it. This doesn't mean that all change is equivalent or that human-caused environmental disruption is somehow natural or acceptable. The current rate of species extinction is orders of magnitude faster than the background rate that characterizes most of Earth's history, and it's occurring without the recovery time that has allowed ecosystems to rebuild after past catastrophes. The lessons from deep time suggest that while life is remarkably resilient over geological timescales, it can be quite fragile over the shorter timescales that matter to human societies. Nevertheless, the long view provided by studying mass extinctions offers reasons for both humility and hope. Humility because it reveals the contingent nature of our own existence and the vulnerability of the complex systems we depend upon. Hope because it demonstrates life's extraordinary capacity for recovery and renewal, even in the face of seemingly impossible odds. As we delve deeper into the mechanisms of extinction and recovery, we begin to appreciate the profound interconnectedness that characterizes Earth's systems. The atmosphere we breathe, the soils that support agriculture, the climate that makes human civilization possible, all bear the fingerprints of billions of years of biological activity. We are not separate from these natural systems, but rather their latest expression, shaped by the same evolutionary forces that have operated throughout Earth's history. This perspective can fundamentally change how we think about our relationship with the natural world. Rather than seeing ourselves as outside observers of natural processes, we can recognize ourselves as participants in the ongoing story of life on Earth. Our species represents the current pinnacle of biological complexity, the product of an unbroken lineage that has survived every catastrophe our planet could produce. We carry within our genes and our neural networks the accumulated wisdom of billions of years of evolutionary experience. Yet with this recognition comes responsibility. We are the first species in Earth's history to develop the capacity for understanding our own evolutionary origins and our impact on global systems. We can read the story of past extinctions in the fossil record, model the complex interactions that drive environmental change, and even predict some aspects of how ecosystems might respond to future perturbations. This knowledge brings with it the potential for conscious choice about the future trajectory of life on Earth. Previous mass extinctions were the result of geological or astronomical forces beyond the control of any living organism. But the current episode of elevated extinction rates is largely the result of human activities, which means it's potentially within our power to influence its course. The lessons from deep time don't provide simple answers to current environmental challenges, but they do offer important guidance. They suggest that maintaining diversity is crucial for resilience, that ecosystem connections are as important as individual species, and that rapid environmental change can trigger cascading effects that are difficult to predict or control. They also remind us that recovery from environmental disruption is possible, but that it typically requires long timescales and may result in very different biological communities than those that existed before. Perhaps most importantly, the deep time perspective encourages us to think beyond the immediate concerns of our own species and our own lifetimes. The story of mass extinctions reveals that the value of biodiversity extends far beyond its immediate utility to human societies. The incredible variety of life forms that have populated our planet represents a vast library of evolutionary solutions to the challenges of existence. Each species that goes extinct takes with it unique genetic information and ecological adaptations that have been refined over millions of years. This genetic and ecological heritage is irreplaceable in any meaningful sense. While evolution can and will continue to generate new forms of complexity and beauty, the specific solutions embodied in current species cannot be recreated if they are lost. The extinction of a species is thus not just a loss to current ecosystems, but a permanent reduction in the information content of the biosphere. Understanding this can help us appreciate why conservation efforts matter, not just for practical reasons, but for deeper philosophical and ethical reasons as well. We are the temporary custodians of an evolutionary heritage that extends back billions of years. The decisions we make about land use, resource consumption, and environmental protection will influence the trajectory of life on Earth for millions of years into the future. This brings us to consider another fascinating aspect of extinction and recovery: the role of chance and contingency in shaping evolutionary outcomes. Each mass extinction event eliminated some lineages while sparing others, but the specific pattern of survival and extinction was influenced by many random factors. The precise timing of environmental changes, the geographic distribution of species, even the particular genetic variants present in surviving populations, all played roles in determining which lineages made it through the crisis. This element of chance means that if we could somehow replay Earth's history, the outcome would likely be very different. Different species might have survived the various extinction events, leading to entirely different evolutionary radiations, and ultimately to a modern biosphere with a completely different cast of characters. The familiar plants and animals of today's world are thus partly the result of contingent historical events that could easily have unfolded differently. This perspective adds another layer of uniqueness and irreplaceability to current biodiversity. The specific collection of species that populate Earth today represents one possible outcome from the vast space of evolutionary possibilities. It's not necessarily the best or most optimal outcome, but it's the particular path that history happened to take through the maze of evolutionary possibilities. Recognizing this contingent nature of evolutionary history can inspire a sense of wonder at the improbability of our current world. The intricate ecosystems that surround us, the complex organisms that share our planet, even our own existence as conscious beings capable of contemplating these questions, all represent outcomes that were far from inevitable. They are the products of a specific historical pathway through billions of years of environmental change and evolutionary response. This realization can also foster a deeper appreciation for the diversity of life that currently exists. Each species represents not just a current solution to ecological challenges, but also a unique historical trajectory through the trials and opportunities presented by Earth's changing environments. The loss of any species thus represents the termination of a unique evolutionary experiment that can never be repeated. As we continue our exploration of these themes, we begin to see how the study of mass extinctions connects to fundamental questions about the nature of life, the meaning of diversity, and our place in the cosmos. These ancient catastrophes serve as natural experiments that reveal principles about how complex systems respond to perturbation, how information is preserved and lost through time, and how creativity and destruction are interwoven in the fabric of natural processes. The story of life's persistence through multiple mass extinctions also speaks to deeper themes about resilience, adaptation, and the nature of complex systems. Despite facing catastrophes that eliminated most species, life has not only survived but has consistently rebuilt complexity and diversity. This pattern suggests that there are fundamental properties of living systems that promote persistence and recovery, even under extreme stress. Understanding these properties has implications that extend beyond biology and paleontology. The same principles that allow ecosystems to recover from mass extinctions may apply to other complex systems, from economic networks to social institutions. The lessons learned from studying biological resilience could inform strategies for building more robust and adaptable human systems. At the same time, the study of mass extinctions reveals the limits of resilience. While life as a whole has persisted through every crisis, individual species, communities, and even entire ecosystems have been permanently lost. This reminds us that resilience is not unlimited, and that there are thresholds beyond which even the most robust systems may collapse irreversibly. These insights take on particular relevance as we consider the environmental challenges facing our modern world. The current episode of biodiversity loss, driven largely by human activities, is occurring at rates that rival or exceed those seen during the great mass extinctions of the past. Understanding how ecosystems have responded to past crises can help us predict how they might respond to current and future stresses. The geological record suggests that, while life as a whole is remarkably resilient, individual ecosystems and species can be quite fragile. The complex relationships that bind modern ecosystems together may be just as vulnerable to disruption as those that collapsed during past extinction events. This vulnerability is compounded by the fact that current environmental changes are occurring against a background of habitat fragmentation and other human impacts that may limit the ability of species to respond adaptively. Yet the same geological record also provides examples of remarkable recovery and innovation. After each mass extinction, life has not only rebuilt diversity, but has often achieved new levels of complexity and sophistication. This creative potential of evolutionary processes remains as strong today as it was in the aftermath of ancient catastrophes. The challenge is ensuring that modern environmental changes occur at rates and scales that allow these creative processes to operate effectively. To truly appreciate the magnitude of life's creative response to catastrophe, let's examine some of the most extraordinary evolutionary innovations that emerged in the wake of mass extinctions. These breakthroughs didn't happen overnight, but rather unfolded over millions of years as surviving lineages explored the vast landscape of evolutionary possibility opened up by extinction. After the Ordovician Silurian extinction, one of the most significant developments was the evolution of jaws in vertebrates. The earliest fish were jawless creatures, somewhat like modern lampreys, that fed by suction or filter feeding. But in the aftermath of the extinction, some lineages began experimenting with new feeding strategies. Over time, gill arches that had originally supported breathing structures were gradually modified into the first primitive jaws. This innovation might seem simple, but it was revolutionary in its implications. Jawed fish could process a much wider variety of food sources than their jawless predecessors. They could bite, chew, and actively hunt prey in ways that had never before been possible in vertebrate evolution. The development of jaws opened up entirely new ecological niches and set the stage for the incredible diversity of vertebrate feeding strategies we see today. From those early jawed fish would eventually arise all other jawed vertebrates, including sharks, bony fish, amphibians, reptiles, birds, and mammals. Every time you bite into food, you're using structures that can trace their evolutionary origin back to those post-extinction innovations in ancient seas. The human jaw, with its complex musculature and precisely arranged teeth, represents millions of years of refinement of that original post-Ordovician breakthrough. The late Devonian extinction, despite its devastating effects on marine ecosystems, created opportunities for one of the most important transitions in the history of life, the evolution of tetrapods, the first four-limbed vertebrates. During the Devonian, some fish had begun developing muscular lobed fins that they could use to prop themselves up in shallow water or even venture briefly onto land. The extinction eliminated many of their aquatic competitors and may have created environmental pressures that favoured this terrestrial ability. In the aftermath of the extinction, these early tetrapods began to exploit terrestrial environments more extensively. They developed stronger limbs, more efficient lungs, and skin that could resist desiccation. Within a few million years, they had given rise to amphibians that could complete their entire life cycles on land, though most still returned to water to reproduce. This terrestrial invasion had cascading effects that transformed the entire planet. Early tetrapods brought vertebrate predation to land for the first time, dramatically affecting terrestrial arthropod communities. They also became important components of food webs that linked aquatic and terrestrial environments. Most significantly for our own story, they established the vertebrate presence on land that would eventually give rise to reptiles, birds, mammals, and ultimately to our own species. The Great Dying at the end of the Permian period, despite being the most severe extinction in Earth's history, was followed by some of the most remarkable evolutionary innovations ever documented. In the devastated world of the early Triassic, surviving archosaur lineages began experimenting with entirely new body plans and lifestyles. Some developed elongated necks for feeding on tall vegetation, others evolved armor plating for protection, and still others began exploring bipedal locomotion. It was during this post-extinction experimentation that the first dinosaurs appeared. These early dinosaurs were small, agile predators that initially represented just one minor component of much more diverse reptilian communities. But they possessed several key innovations that would prove crucial for their later success. They had evolved more efficient upright postures that reduced energy costs of locomotion, more sophisticated temperature regulation that allowed greater activity levels, and complex social behaviours that enhanced their survival and reproductive success. Perhaps most remarkably, some dinosaur lineages began experimenting with powered flight. The evolution of birds from small theropod dinosaurs represents one of the most extraordinary transitions in vertebrate history. Flight had evolved before in insects and pterosaurs, but the avian solution was unique in its combination of sophisticated aerodynamics, metabolic efficiency, and behavioural complexity. The development of flight in birds involved numerous anatomical innovations: hollow bones that reduced weight while maintaining strength, asymmetrical feathers that provided lift and control, specialised respiratory systems that supported the high metabolic demands of powered flight, and complex neurological adaptations that enabled the precise motor control required for aerial manoeuvring. Each of these innovations required millions of years of gradual refinement, but together they produced flying machines of extraordinary sophistication. Modern birds can navigate thousands of miles using magnetic fields and celestial cues, perform aerial acrobatics that surpass any human aircraft, and achieve energy efficiencies that engineers can only dream of replicating. All of this complexity traces back to evolutionary experimentation that began in the aftermath of the Permian extinction, when surviving archosaurs were exploring new ways of making a living in a devastated world. The Cretaceous-Paleogene extinction, which eliminated non-avian dinosaurs, created opportunities for an even more dramatic evolutionary radiation, the rise of modern mammals. During the Mesozoic era, mammals had remained relatively small and inconspicuous, constrained by competition from dinosaurs and other reptilian groups. But in the aftermath of the extinction, they suddenly found themselves in a world filled with vacant ecological opportunities. The mammalian response to this opportunity was swift and dramatic. Within just 10 million years of the extinction, mammals had diversified into forms as different as early primates, primitive whales, the first bats, and the ancestors of modern ungulates. Each group was exploring different solutions to the challenges of life in the post-dinosaur world, and many of their innovations surpassed anything that had existed during the Mesozoic. Consider the evolution of echolocation in bats, one of the most sophisticated sensory systems in the animal kingdom. Early bats developed the ability to navigate and hunt in complete darkness, using high-frequency sound waves and their returning echoes. This biological sonar system allows modern bats to detect wires as thin as human hair, distinguish between different types of insects on the wing, and navigate through dense forests at high speed in complete darkness. The neurological processing required for echolocation rivals the complexity of human language centers. Bats must produce precisely timed sound pulses, analyze the complex patterns of returning echoes, construct three-dimensional mental maps of their environment, and coordinate all of this with rapid flight maneuvers. The fact that such complexity evolved from small, generalized mammals in just a few million years after the Cretaceous extinction demonstrates the incredible creative potential of evolutionary processes when freed from competitive constraints. Equally remarkable was the return of mammals to aquatic environments and the evolution of whales. The transition from small terrestrial mammals to fully aquatic giants like modern blue whales represents one of the most dramatic evolutionary transformations ever documented. Early whale ancestors were wolf-sized predators that hunted along shorelines. Over roughly 15 million years, their descendants became increasingly aquatic, developing streamlined bodies, powerful tail flukes, sophisticated echolocation systems, and the complex social behaviors that characterize modern cetaceans. Modern whales possess cognitive abilities that rival those of primates in some respects. They have complex social structures, sophisticated communication systems, cultural traditions that are passed between generations, and self-awareness that has been demonstrated through mirror recognition tests. Some whale songs contain structured elements that resemble human music with themes, variations, and even what appear to be rhyming patterns. The largest whales have brains that weigh over 15 pounds and contain billions of neurons, arranged in structures that suggest remarkable intelligence. All of this neural complexity evolved from the simple mammalian brain plan that survived the Cretaceous extinction. The transformation from small, ground-dwelling insectivores to ocean-dwelling giants with complex cognitive abilities illustrates the extraordinary plasticity of evolutionary processes and the remarkable potential for innovation that can emerge from catastrophic disruption. But perhaps the most significant post-extinction innovation from our human perspective was the evolution of enhanced cognitive abilities in various mammalian lineages. The ecological opportunities created by dinosaur extinction allowed some mammals to explore increasingly complex social behaviors and environmental interactions. This led to the evolution of larger brains, more sophisticated sensory processing, and eventually to the cognitive capabilities that characterize modern primates. The primate lineage that eventually gave rise to humans began as small arboreal creatures that exploited the three-dimensional environment of early Cenozoic forests. Life in the trees placed a premium on spatial awareness, hand-eye coordination, and the ability to make rapid decisions about which branches would support body weight. These demands drove the evolution of enhanced visual processing, improved motor control, and increased brain size relative to body size. Over millions of years, these cognitive enhancements were further refined by the complex social dynamics that characterize primate groups. Living in social communities required abilities to recognize individuals, remember past interactions, predict the behavior of others, and navigate complex networks of cooperation and competition. These social pressures drove the evolution of even larger brains and more sophisticated cognitive abilities. The eventual emergence of human intelligence represents the culmination of this post-extinction evolutionary trajectory. Our species possesses cognitive abilities that are qualitatively different from anything that existed during the Mesozoic era. We can engage in abstract reasoning, create symbolic representations of reality, pass complex information between generations through language and culture, and even contemplate our own evolutionary origins. From the perspective of deep time, human intelligence represents just the latest in a long series of post-extinction innovations. Like the evolution of jaws, tetrapod limbs, flight, and echolocation, the development of human cognitive abilities was made possible by the ecological opportunities created by mass extinction. Without the Cretaceous impact that eliminated dinosaurs, mammals might have remained small, nocturnal creatures, and the particular type of intelligence that characterizes our species might never have evolved. This realization adds another layer of contingency to our understanding of human existence. Not only are we the products of a specific historical pathway through billions of years of evolution, but our very capacity for consciousness and self-reflection depends on catastrophic events that occurred long before our species existed. The asteroid impact that ended the age of dinosaurs was thus not just a geological event, but a necessary precondition for the eventual emergence of minds capable of understanding that very impact. As we continue to explore these post-extinction innovations, we begin to see common patterns in how evolution responds to catastrophic opportunity. In each case, surviving lineages didn't simply return to their previous ways of life, but instead explored entirely new evolutionary possibilities. The vacant ecological space left by extinction became a laboratory for biological experimentation, leading to innovations that often surpassed the complexity and sophistication of anything that had existed before. This pattern suggests that mass extinctions, despite their devastating immediate effects, may actually accelerate the long-term evolution of complexity and diversity. By periodically clearing away established biological communities, extinctions create opportunities for evolutionary breakthroughs that might otherwise be prevented by competitive exclusion. Each extinction thus represents not just an ending, but also a beginning, a reset that allows evolution to explore new regions of biological possibility space. The innovations that emerge from these post-extinction radiations often have emergent properties that couldn't have been predicted from the characteristics of the surviving ancestors. The complex cognitive abilities of modern mammals, for example, emerged from small-brained survivors whose intelligence was unremarkable by Mesozoic standards. The sophisticated flight capabilities of birds arose from terrestrial dinosaurs that showed no obvious pre-adaptations for aerial life. The echolocation abilities of bats evolved from mammals with conventional hearing and vision. This unpredictability of evolutionary outcomes reflects the creative nature of natural selection when operating in novel environments. Without the constraints imposed by existing biological communities, evolution can explore combinations of traits and ecological strategies that would be impossible under normal circumstances. The result is often the emergence of entirely new types of organisms with capabilities that represent genuine evolutionary novelty. Understanding this creative aspect of post-extinction evolution provides important insights into the nature of evolutionary processes more generally. Evolution is not simply a process of gradual optimization within existing parameters, but rather a creative force capable of generating genuine novelty and complexity. Mass extinctions reveal this creative potential by removing the constraints that normally limit evolutionary exploration. This perspective has implications for how we think about evolution's future trajectory as well. If current environmental changes do trigger another mass extinction, the long-term consequences may not be simply negative. While the immediate losses would be tragic and irreversible, the aftermath might also create opportunities for evolutionary innovations that could lead to new forms of biological complexity and diversity. Of course, this long-term perspective doesn't diminish the importance of current conservation efforts. The timescales involved in post-extinction recovery are measured in millions of years, far longer than any human timescale that matters for practical decision-making. From the perspective of human societies and the ecosystems we depend upon, mass extinction is an unmitigated catastrophe, regardless of its eventual evolutionary consequences. But understanding evolution's creative response to past catastrophes can provide perspective on the resilience of life more generally. Even if current environmental changes do trigger major disruptions to Earth's biosphere, the fundamental processes that have allowed life to persist and diversify for billions of years remain intact. The genetic mechanisms that enable adaptation, the ecological processes that allow community assembly, and the evolutionary forces that drive innovation and complexity all continue to operate. This doesn't mean that recovery from major environmental disruption would be easy or rapid. The geological record shows that rebuilding ecosystem complexity after mass extinction typically requires millions of years, and often results in biological communities that are very different from those that existed before. But it does suggest that life's capacity for recovery and innovation remains as strong today as it was in the aftermath of ancient catastrophes. As we reflect on these patterns of destruction and renewal, innovation and recovery, we begin to appreciate the profound resilience that characterizes life on Earth. This resilience doesn't come from any single species or ecosystem, but rather from the fundamental properties of living systems, their diversity, their capacity for rapid reproduction and genetic change, and their ability to exploit almost any available source of energy and materials. These properties have allowed life to persist through every catastrophe that Earth's dynamic systems have produced. Volcanic eruptions, asteroid impacts, climate changes, atmospheric transformations, and countless other environmental upheavals have all failed to eliminate life completely. Instead, each crisis has become an opportunity for evolutionary experimentation and innovation. The story of post-extinction evolution also reveals the importance of preserving diversity not just for its own sake, but as a reservoir of evolutionary potential. The remarkable innovations that followed each mass extinction emerged from seemingly unremarkable survivors whose hidden capabilities only became apparent when environmental changes created new opportunities for their expression. This suggests that even species that seem unimportant or insignificant today may harbour evolutionary potential that could prove crucial under future environmental conditions. This principle applies not just to individual species, but to entire ecosystems and biological communities. The complex networks of interactions that characterize healthy ecosystems represent vast repositories of evolutionary information and potential. Disrupting these networks doesn't just eliminate current biodiversity, but also reduces the raw material available for future evolutionary innovation. From this perspective, conservation efforts take on significance that extends far beyond immediate practical concerns. By preserving current biodiversity and ecosystem complexity, we're not just protecting resources that are useful to human societies today, but also maintaining the evolutionary potential that could give rise to future biological innovations. We're preserving the library of genetic and ecological information that represents billions of years of evolutionary experimentation and discovery. As our journey through deep time continues, we find ourselves contemplating not just the past, but also the future. The same processes that have shaped life's response to ancient catastrophes continue to operate today, though on timescales that are often difficult for human minds to grasp. Evolution continues to generate new species, new ecological relationships, and new forms of complexity, even as environmental changes driven by human activities threaten existing biological communities. Understanding the deep time perspective on extinction and recovery can help us appreciate both the fragility and the resilience of the living world. Individual species and ecosystems can be remarkably vulnerable to rapid environmental change, as demonstrated by the massive losses that characterized each mass extinction event. But life as a whole has proven extraordinarily resilient, consistently finding ways to survive, adapt, and ultimately thrive in the face of seemingly impossible challenges. This dual nature of fragility and resilience characterizes not just biological systems, but complex systems more generally. The same principles that govern ecosystem responses to environmental perturbation also apply to social systems, economic networks, and technological infrastructures. Understanding how complex systems maintain stability while also retaining the capacity for adaptive change is crucial for building resilient human societies in an era of rapid environmental and social transformation. As we stand at this particular moment in Earth's history, roughly 66 million years after the last great mass extinction, we find ourselves in a unique position to observe and potentially influence the trajectory of life on our planet. For the first time in Earth's 4.5 billion year history, a single species has developed the capacity to understand the deep time processes that have shaped the biosphere and to consciously affect the future course of evolution. This unprecedented situation raises profound questions about our role as conscious participants in Earth's ongoing evolutionary story. Are we simply another species that happened to evolve intelligence, destined to follow the same patterns of rise and eventual extinction that have characterized every other dominant group in Earth's history? Or does our capacity for understanding and foresight give us the ability to transcend these patterns and become conscious stewards of the planet's biological heritage? The geological record offers both sobering reminders and reasons for hope as we consider these questions. On one hand, the history of life shows us that no species, no matter how successful or dominant, persists forever. Every lineage that has ever existed has either gone extinct or evolved into something sufficiently different to be considered a new species. From this perspective, human extinction is not a matter of if, but when, and our current concerns about environmental degradation may simply represent the early stages of our own eventual demise. But the deep time perspective also reveals something unprecedented about our current situation. Never before has a species developed the capacity to read its own evolutionary history in the fossil record, to understand the global consequences of its actions, and to consciously modify its behavior based on long-term projections. We are the first species capable of learning from the mass extinctions of the past and potentially preventing our own contribution to a future one. This capacity for conscious foresight represents a genuinely new phenomenon in the history of life on Earth. While many organisms show sophisticated behavioral adaptations to environmental changes, and some even exhibit what might be called rudimentary planning abilities, no previous species has been able to comprehend the global, long-term consequences of its actions and adjust its behavior accordingly. We are the first species to understand concepts like sustainability, conservation, and stewardship, and the first to have the technological capacity to implement these concepts on a planetary scale. Whether we will actually use these capabilities effectively remains to be seen. The current trajectory of human environmental impact suggests that we are indeed triggering the sixth mass extinction, with species disappearing at rates that rival or exceed those seen during the great dying events of the past. Climate change, habitat destruction, pollution, and other human impacts are creating environmental stresses that many species cannot survive. Yet there are also signs that human consciousness is beginning to grapple seriously with these challenges. The development of conservation biology as a scientific discipline, the establishment of protected areas around the world, the growing awareness of climate change and its consequences, and the emergence of sustainable technologies all suggest that our species is beginning to understand its role as a planetary force and to take responsibility for that role. The question is whether these conscious responses will develop quickly enough and prove effective enough to prevent the worst outcomes. The timescales involved in environmental change are often much shorter than those involved in cultural and technological adaptation. Climate change, species extinctions, and ecosystem disruptions are occurring over decades and centuries, while the development of sustainable societies and technologies may require much longer periods. This mismatch between the timescales of environmental change and human adaptation creates what scientists call a temporal trap. Even if we eventually develop the wisdom and technologies needed to live sustainably on Earth, we may trigger irreversible environmental changes before those developments can be implemented. The lag time between cause and effect in Earth systems means that the consequences of current actions may not become fully apparent until it's too late to prevent them. Understanding this temporal trap is crucial for appreciating both the urgency of current environmental challenges and the importance of the decisions we make in the coming decades. Unlike previous mass extinctions, which were triggered by geological or astronomical forces beyond the control of any living organism, the current extinction crisis is largely within human control. This means that the future trajectory of life on Earth depends, to an unprecedented degree, on the choices made by a single species during a relatively brief period of geological time. The responsibility that comes with this realization is both inspiring and daunting. We have the opportunity to become the first species in Earth's history to consciously prevent a mass extinction rather than simply survive one. But we also bear the burden of knowing that our failures could trigger an extinction event that would eliminate millions of other species and fundamentally alter the trajectory of evolution for millions of years to come. As we consider this responsibility, it's worth reflecting on what the deep time perspective tells us about the value and significance of our current biological heritage. Each species that exists today represents the culmination of an unbroken lineage that stretches back billions of years. Every organism carries within its genetic code information that has been refined through countless generations of natural selection, representing solutions to the challenges of survival and reproduction that have been tested against the full range of environmental conditions that Earth can produce. This genetic heritage is not just historically significant, but also practically valuable for addressing current and future challenges. Modern medicine draws heavily on compounds and mechanisms discovered in other organisms. Agricultural sustainability depends on maintaining genetic diversity in crop species and their wild relatives. Biotechnology increasingly relies on biological processes and structures as inspiration for new materials and technologies. But beyond these practical considerations, biological diversity represents something even more profound, a vast library of evolutionary experiments and discoveries that embodies billions of years of problem solving by natural selection. Each species represents a unique solution to the challenge of existence, a particular way of extracting energy from the environment, processing information, reproducing, and interacting with other organisms. The loss of species through extinction thus represents not just a reduction in current biodiversity, but a permanent loss of evolutionary information that can never be recovered. Unlike human libraries, which can be rebuilt if destroyed, the library of genetic and ecological information embodied in Earth's species cannot be reconstructed once it's lost. Each extinction eliminates a unique evolutionary experiment that took millions of years to develop and can never be repeated. This irreversibility of extinction gives special significance to our current moment in Earth's history. We are living during what may be one of the most biodiverse periods in our planet's history, certainly the most biodiverse period since the Cretaceous extinction eliminated the dinosaurs. The choices we make about how to manage this biodiversity will determine how much of Earth's evolutionary heritage survives into the future. From the deep time perspective, our current responsibility is thus not just to our own species or even to current ecosystems, but to the entire evolutionary future of life on Earth. The species that survive the current extinction crisis will be the ancestors of all future biodiversity. By influencing which species survive and which go extinct, we're effectively determining the raw material that will be available for all future evolution. This realization can be either paralyzing or motivating, depending on how we choose to respond to it. The scale of the responsibility can seem overwhelming, beyond the capacity of any single species to handle effectively. But it can also inspire us to rise to the challenge, to use our unprecedented cognitive abilities and technological capabilities to become worthy stewards of our planet's biological heritage. The tools we need for this stewardship already exist, at least in preliminary form. We have the scientific knowledge to understand ecosystem functioning and species requirements. We have the technological capabilities to monitor environmental changes and implement conservation strategies. We have economic and political systems that, while imperfect, provide mechanisms for coordinating action on large scales. Most importantly, we have the cognitive abilities to understand long-term consequences and modify our behavior accordingly. What we often lack is the collective will to implement these tools effectively. The same cognitive abilities that allow us to understand global environmental processes also make us susceptible to short-term thinking, tribal conflicts, and the difficulty of coordinating action across large populations. The challenge is not primarily technical or scientific, but rather social and psychological. How do we organize human societies to respond effectively to long-term global challenges? The deep time perspective suggests that this challenge is not unprecedented, even if its specific form is new. Throughout Earth's history, life has faced the challenge of coordinating complex systems in the face of environmental change. Ecosystems must maintain stability while retaining the flexibility to adapt to new conditions. Species must balance the conflicting demands of current survival and long-term reproductive success. Even individual organisms must coordinate the activities of billions of cells to maintain function while allowing for growth and adaptation. In each case, the solution has involved developing hierarchical organization, feedback mechanisms, and systems that can maintain stability while allowing for adaptive change. Human societies are experimenting with similar organizational innovations, from international environmental agreements to local sustainability initiatives to new economic models that account for environmental costs. The question is whether these social innovations will develop quickly enough and prove effective enough to address the current environmental crisis. Unlike biological evolution, which operates over millions of years, cultural evolution can operate over decades or even years. This gives us reason for hope that human societies can adapt to environmental challenges much more quickly than biological systems alone. But cultural evolution also faces its own constraints and limitations. Social institutions can be resistant to change, especially when that change challenges established interests or requires sacrifices from current generations for the benefit of future ones. The same cognitive biases that helped our ancestors survive in small social groups can hinder our ability to respond effectively to global, long-term challenges. Understanding these constraints can help us develop more effective strategies for promoting the social changes needed to address environmental challenges. Rather than simply hoping that people will spontaneously adopt more sustainable behaviors, we can design institutions and incentives that make sustainable choices easier and more attractive. Rather than relying solely on individual responsibility, we can create social systems that channel individual actions toward collective goals. The mass extinctions of the past offer additional insights into effective strategies for survival and recovery. The species that survived these catastrophes typically shared certain characteristics. They were generalists rather than specialists. They had flexible diets and behaviors. They could tolerate a wide range of environmental conditions, and they maintained large, genetically diverse populations. These survival characteristics translate into conservation strategies that can help maximize the number of species that survive current environmental changes. Protecting habitat corridors that allow species to migrate as conditions change, maintaining genetic diversity within populations, protecting species that serve as indicators of ecosystem health, and focusing conservation efforts on adaptable species that can serve as seeds for future recovery. But perhaps the most important lesson from past extinctions is the value of maintaining diversity at all levels, from genetic diversity within populations to species diversity within ecosystems to ecosystem diversity across landscapes. This diversity provides the raw material for adaptive responses to environmental change and increases the probability that some lineages will possess the characteristics needed to survive whatever challenges the future might bring. For human societies, this translates into the importance of maintaining cultural diversity, technological diversity, and economic diversity. Just as biological monocultures are vulnerable to environmental perturbations, human monocultures may be vulnerable to social, economic, or technological disruptions. Maintaining multiple approaches to organization, technology, and problem-solving increases our collective resilience and adaptability. The deep time perspective also suggests the importance of thinking beyond crisis management to long-term flourishing. The species that emerged from past mass extinctions didn't just survive, they often achieved new levels of complexity and sophistication. The challenge for human societies is not just to survive current environmental challenges, but to use them as opportunities for developing more sustainable and equitable ways of living on Earth. This requires thinking about environmental challenges not just as problems to be solved, but as opportunities for innovation and improvement. Climate change, for example, is driving the development of renewable energy technologies that may prove superior to fossil fuels in many respects. The challenge of feeding a growing global population is spurring innovations in agriculture that could improve food security while reducing environmental impact. The need to protect biodiversity is encouraging new approaches to land use that could enhance both conservation and human well-being. These innovations represent the beginning of what could become a major transition in human civilization, comparable to the agricultural revolution or the industrial revolution. Just as those earlier transitions transformed human societies and their relationship with the environment, the current sustainability transition could lead to fundamentally new ways of organizing human activities and interacting with natural systems. The success of this transition will depend partly on our ability to learn from the deep time lessons embedded in Earth's history. The mass extinctions of the past show us that environmental systems can reach tipping points where gradual change becomes rapid collapse. They also show us that recovery is possible, but that it typically requires long timescales and often results in very different biological communities than those that existed before. Understanding these patterns can help us avoid the worst outcomes while positioning ourselves to take advantage of new opportunities. By acting before environmental systems reach critical tipping points, we may be able to guide change rather than simply react to it. By maintaining diversity and flexibility in our social and technological systems, we can increase our capacity to adapt to whatever changes do occur. The deep time perspective also reminds us that our current challenges, while serious and urgent, are part of a much larger story that will continue long after our current crisis is resolved. Life on Earth has survived every catastrophe that our planet's dynamic systems have produced, and it will continue to evolve and diversify long after our species has passed into the fossil record. Understanding our place in this larger story can provide both humility about our limitations and inspiration about our potential contributions. We have the opportunity to become the first species in Earth's history to consciously guide the trajectory of evolution on a planetary scale. This doesn't mean controlling or directing every aspect of natural processes, but rather understanding our role as a planetary force and taking responsibility for that role. We can choose to be a force for conservation and sustainable development rather than destruction and depletion. The choices we make in the coming decades will determine whether future paleontologists, if any exist, will classify our era as the beginning of the sixth mass extinction, or as the time when a species first learned to live sustainably on its planet. This is perhaps the most significant decision that any species has ever faced, and its outcome will influence the trajectory of life on Earth for millions of years to come. To fully appreciate the magnitude of this moment, let's expand our perspective beyond Earth itself and consider our planet's story within the larger context of the cosmos. When we view Earth's mass extinctions against the backdrop of the universe as a whole, we begin to understand just how extraordinary our planet's biological heritage truly is, and how rare the emergence of conscious intelligence may be throughout the cosmos. Our Sun is just one of roughly 400 billion stars in the Milky Way galaxy, which is itself just one of hundreds of billions of galaxies in the observable universe. Current estimates suggest there may be trillions of planets throughout the cosmos, and many of these likely exist in the habitable zones around their stars where liquid water could exist. Yet despite this vast number of potential homes for life, we have found no definitive evidence for life anywhere else in the universe. This apparent absence of detectable life elsewhere, sometimes called the Fermi paradox, becomes even more puzzling when we consider how quickly life appeared on Earth after conditions became suitable. The oldest evidence for life on our planet dates back nearly 4 billion years, appearing within just a few 100 million years after Earth's surface cooled enough to support liquid water. This suggests that the emergence of simple life may be relatively easy under the right conditions. But the progression from simple life to complex multicellular organisms took much longer. For roughly 2.5 billion years, Earth was inhabited only by microscopic single-celled organisms. The evolution of complex multicellular life required a series of unlikely events, including the development of photosynthesis, the Great Oxidation Event that transformed Earth's atmosphere, and the evolution of eukaryotic cells through the merger of different bacterial lineages. Even after multicellular life appeared, the evolution of intelligence took hundreds of millions of additional years and was repeatedly interrupted by mass extinction events. Each of these catastrophes could have permanently derailed the development of complex cognition. If the asteroid that ended the Cretaceous had been slightly larger, or if the Permian volcanism had been slightly more severe, the trajectory towards intelligence might have been permanently interrupted. The fact that intelligence did eventually emerge on Earth, despite these obstacles, suggests that conscious beings may be extraordinarily rare in the universe. We may be among the first intelligences to arise in our cosmic neighborhood, or possibly even in the entire galaxy. This possibility adds another layer of significance to our current responsibility as stewards of Earth's biological heritage. If conscious intelligence is indeed rare in the cosmos, then our planet may represent something truly precious, a rare flowering of awareness and understanding in an otherwise unconscious universe. The loss of Earth's biodiversity would then represent not just a planetary tragedy, but a cosmic one, the destruction of something that may be unique in our region of space and time. This cosmic perspective doesn't diminish the importance of our earthly concerns, but rather amplifies them. If we are indeed among the only conscious beings in our cosmic neighborhood, then our decisions about how to manage Earth's biosphere take on significance that extends far beyond our own planet. We may be making choices not just for Earth's future, but for the future of consciousness itself in this part of the universe. The rarity of intelligence also suggests that if we can learn to live sustainably on Earth, we may have opportunities to spread life and consciousness to other worlds. Several space agencies and private organizations are already working on technologies that could enable human settlement of Mars, and more ambitious proposals envision terraforming planets or establishing colonies and artificial habitats throughout the solar system. From the deep time perspective, such expansion could represent the next great transition in the history of life, comparable to the original colonization of land by early tetrapods or the evolution of flight in birds and insects. For the first time in Earth's history, life could become truly spacefaring, able to survive and thrive beyond the boundaries of its home planet. This possibility adds yet another dimension to our current environmental challenges. If we can successfully navigate the current extinction crisis and learn to live sustainably on Earth, we may be taking the first steps toward becoming a truly cosmic civilization, one capable of spreading life and intelligence throughout the galaxy. But if we fail to address our environmental problems, we may not only trigger a mass extinction on Earth, but also eliminate the possibility of life expanding beyond our planet. The deep time perspective suggests that such expansion may be not just an opportunity, but an eventual necessity. While Earth has proven remarkably resilient over billions of years, it will not remain habitable forever. Our sun is gradually becoming brighter as it ages, and in about 1 billion years, it will be hot enough to boil away Earth's oceans. Long before that, various astronomical events, from asteroid impacts, nearby supernova explosions, could threaten life on our planet. If life is to survive these cosmic hazards, it must eventually spread beyond Earth. The intelligence that has emerged through billions of years of evolution on our planet may thus represent not just a remarkable achievement, but also life's best hope for long-term survival in an often hostile universe. By developing the technology and wisdom needed to live sustainably on multiple worlds, we could help ensure that the remarkable story of life that began on Earth continues for billions of years into the future. But this cosmic destiny, if it exists, can only be achieved if we first learn to live wisely on our home planet. The same technologies and social innovations needed for sustainability on Earth, renewable energy, closed-loop resource cycling, sophisticated ecosystem management, would also be essential for establishing sustainable colonies on other worlds. The wisdom needed to balance human needs with environmental protection on Earth would be equally necessary for managing artificial ecosystems in space. In this sense, our current environmental challenges can be seen not just as problems to be solved, but as training for an even greater challenge, learning to be responsible stewards of life throughout the cosmos. The mass extinctions of Earth's past offer crucial lessons for this cosmic responsibility, showing us both the fragility of complex life and its remarkable capacity for recovery and innovation. As we continue our journey through deep time, it's worth reflecting on how the story of mass extinctions connects to our individual human experience. We are each temporary arrangements of matter and energy, briefly organized into conscious, experiencing beings before returning to the cosmic recycling process that has operated since the beginning of time. The atoms that make up our bodies were forged in ancient stellar furnaces and have been part of countless other organisms before becoming part of us. This material continuity connects us directly to the deep history we've been exploring. The carbon in our bodies may once have been part of a Permian forest or a Cretaceous dinosaur. The oxygen we breathe was produced by billions of photosynthetic organisms over millions of years. The calcium in our bones may have once formed the shells of ancient marine creatures that lived and died in Paleozoic seas. But beyond this material connection, we are also connected to the past through the information encoded in our genes. Every cell in our bodies carries DNA that represents an unbroken chain of inheritance, stretching back to the earliest life on Earth. This genetic heritage includes not just the basic molecular machinery of life, but also the accumulated wisdom of billions of years of natural selection. The fact that we exist at all means that every one of our ancestors, through all of those billions of years, successfully survived and reproduced. They weathered countless environmental changes, avoided predators, found food and mates, and passed their genes on to the next generation. We are the current expression of this unbroken chain of success, the living embodiment of nearly 4 billion years of evolutionary problem solving. This realization can provide a profound sense of connection to the natural world and to the deep history of life on Earth. We are not separate from nature, but rather nature's way of becoming conscious of itself. Through us, the universe has developed the capacity for self-reflection, for understanding its own history and contemplating its own future. We are the cosmos thinking about itself. This perspective can transform how we understand our place in the world and our relationship to other forms of life. Rather than seeing ourselves as outside observers of natural processes, we can recognize ourselves as participants in the ongoing evolution of complexity and consciousness. Our thoughts, our emotions, our creative endeavors, our scientific discoveries all represent the cutting edge of cosmic evolution, the universe's latest experiments in information processing and pattern recognition. The mass extinctions we've explored tonight represent crucial chapters in this cosmic story of increasing complexity. Each extinction eliminated some forms of organized complexity, while creating opportunities for new and often more sophisticated forms to emerge. The intelligence that eventually arose from this process represents perhaps the most complex phenomenon we know of in the universe, certainly the most complex phenomenon on Earth. Yet this complexity remains fragile and contingent. The same environmental forces that triggered past mass extinctions could potentially eliminate human civilization and even human consciousness. Nuclear war, climate change, asteroid impacts, or other catastrophes could end the remarkable experiment in cosmic self-awareness that our species represents. This fragility gives special poignancy to our current moment in cosmic history. We may be living during a brief window when the universe has become conscious of itself through human intelligence, But before that consciousness has spread widely enough to ensure its long-term survival, the decisions we make about sustainability, technology, and space exploration may determine whether this window closes quickly or opens into a much longer period of cosmic awareness. The deep time perspective suggests that consciousness, once it emerges, has a responsibility to persist and spread. If we are indeed among the first intelligences to arise in our cosmic neighborhood, then we bear a special obligation to ensure that consciousness survives and flourishes. This obligation extends beyond our own species to include the entire web of life that gave rise to consciousness and continues to support it. From this cosmic perspective, conservation efforts take on significance that extends far beyond their immediate practical benefits. By protecting Earth's biodiversity, we are preserving the biological foundation that makes consciousness possible. By developing sustainable technologies, we are creating the tools that could allow consciousness to spread beyond Earth. By learning to manage complex systems wisely, we are developing the skills that may be necessary for long-term cosmic survival. The story of mass extinctions also offers hope for our cosmic future. Despite facing catastrophes that eliminated most species, life has consistently demonstrated remarkable resilience and creativity. Each extinction has been followed by evolutionary innovations that often exceeded anything that existed before. If we can navigate our current environmental challenges successfully, we may trigger a similar burst of innovation that could transform our species and our relationship with the cosmos. Already, we can see the beginnings of such innovation in fields ranging from biotechnology to artificial intelligence to space exploration. The same crisis that threatens current biodiversity is also driving technological developments that could revolutionize how we understand and interact with living systems. Genetic engineering could allow us to restore extinct species or create entirely new forms of life adapted to extreme environments. Artificial intelligence could amplify human cognitive abilities and help us understand complex systems that are beyond current human comprehension. These technologies could be tools for creating a more sustainable and expansive future, but they also represent new sources of risk and uncertainty. The same genetic engineering techniques that could help restore ecosystems could also create dangerous new pathogens. The artificial intelligence systems that could help us manage complex environmental problems could also pose existential risks if not developed carefully. Navigating these opportunities and risks will require wisdom that draws on both scientific understanding and deeper philosophical reflection about the nature and purpose of consciousness in the cosmos. The deep time perspective provided by studying mass extinctions can contribute to this wisdom by helping us understand the long-term consequences of our actions and the broader context within which our decisions unfold. Perhaps most importantly, the story of mass extinctions reminds us that change is the fundamental character of existence. The static, stable world that we often imagine as normal is actually quite unusual from a geological perspective. Throughout Earth's history, environmental conditions have been constantly shifting, and life has been constantly adapting to new challenges and opportunities. Our current environmental crisis, serious and requiring urgent attention, is thus part of this larger pattern of constant change. The question is not whether change will occur, but rather how we will respond to it. Will we be passive victims of environmental transformation, like many species during past mass extinctions? Or will we be active participants, using our intelligence and technology to shape change in positive directions? The deep time perspective suggests that active participation is both possible and necessary. Unlike other species, we have the cognitive tools to understand long-term trends and consequences. Unlike previous generations of humans, we have technologies that could allow us to live sustainably and even improve environmental conditions. Unlike any species in Earth's history, we have the potential to spread life beyond our home planet and ensure its long-term survival against cosmic hazards. Whether we realize this potential depends on choices we make in the coming decades and centuries. These choices will determine not just the fate of current species and ecosystems, but the long-term trajectory of consciousness and complexity in the universe. From the deep time perspective, We are living through one of the most significant moments in cosmic history, a time when the universe's capacity for self-awareness hangs in the balance. This realization can be either overwhelming or inspiring, depending on how we choose to respond to it. The responsibility is enormous, but so is the opportunity. We have the chance to become worthy descendants of the billions of organisms that survived countless catastrophes to give us this moment of cosmic awareness. We have the opportunity to ensure that their legacy continues not just on Earth, but throughout the cosmos. The story of mass extinctions, for all its darkness and destruction, is ultimately a story of life's triumph over seemingly impossible odds. It shows us that resilience, creativity, and adaptation are fundamental characteristics of living systems. It demonstrates that even the most catastrophic setbacks can become opportunities for breakthrough innovations. Most importantly, it reveals that consciousness itself represents the universe's greatest achievement, the culmination of billions of years of increasing complexity and organization. As we prepare to bring our journey through deep time toward a close, we can take comfort in this larger pattern of cosmic evolution towards greater complexity and awareness. We are part of something much larger than ourselves, participants in a story that began with the first simple cells billions of years ago and continues to unfold through our thoughts, our dreams, our scientific discoveries, and our creative endeavors. The mass extinctions of the past remind us that this story is not guaranteed to continue, but they also show us that life has an extraordinary capacity for persistence and renewal. By understanding our place in this cosmic narrative, we can find both the humility to recognize our limitations and the inspiration to use our remarkable capabilities wisely and well. Now, as we draw closer to the gentle conclusion of our evening's exploration, let's turn inward and consider how this deep time awareness might transform our daily experience of being alive. When we truly absorb the lessons of Earth's ancient catastrophes, something shifts in how we perceive the ordinary moments of our lives. The simple act of breathing connects us to atmospheric processes that have been operating for billions of years. The warmth of sunlight on our skin links us to nuclear fusion reactions that have been powering life on Earth since its beginning. Consider the extraordinary improbability of this very moment. You're experiencing consciousness, that most mysterious and precious phenomenon in the known universe, in a body composed of elements forged in stellar cores billions of years ago. The particular arrangement of atoms that constitutes your brain has never existed before, and will never exist again in exactly the same form. You're a temporary eddy in the cosmic flow of matter and energy, a brief opportunity for the universe to experience itself subjectively. This perspective doesn't diminish the importance of human concerns and experiences, but rather places them within a larger context that can infuse even ordinary moments with wonder. The coffee you drink in the morning contains water molecules that may have fallen as rain on Jurassic ferns or filled the cells of Cretaceous marine reptiles. The oxygen you breathe was produced by countless generations of photosynthetic organisms, many of which lived and died hundreds of millions of years before the first human walked the Earth. Your genetic heritage connects you to every organism that has ever lived. The basic molecular machinery that powers your cells is fundamentally identical to that found in bacteria, plants, fungi, and every other form of life on Earth. At the molecular level, all life shares a common ancestry that traces back to the earliest cells that somehow learned to capture energy and reproduce in the hostile environment of the early Earth. Yet, despite this deep unity, you are also absolutely unique. The specific combination of genes you carry has never existed before, and, unless you have an identical twin, will never exist again. Your particular pattern of neural connections, shaped by your unique experiences and interactions, creates a form of consciousness that is entirely your own. You represent a singular experiment in awareness, a unique way that the cosmos has organized itself to observe and understand its own nature. This dual nature of unity and uniqueness extends to all life on Earth. Every species shares the same basic biochemical foundation, yet each represents a distinct solution to the challenge of existence. Every individual organism carries the same fundamental genetic code, yet each expresses that code in ways that create unique patterns of form and behaviour. Life is simultaneously one and many, unified at its foundation yet endlessly diverse in its expressions. The mass extinctions we've explored tonight reveal both aspects of this paradox. They show us how vulnerable individual species and ecosystems can be to environmental change, yet they also demonstrate the remarkable resilience of life as a whole. Even the most severe extinction events have failed to eliminate life entirely, and each has been followed by evolutionary radiations that generated new forms of complexity and beauty. This pattern of destruction and renewal, ending and beginning, loss and discovery, appears to be fundamental to how complex systems evolve over time. It's not just biological systems that show this pattern. Human cultures rise and fall, technological paradigms emerge and become obsolete, and even individual human lives follow cycles of growth, maturity, decline, and renewal. The same forces that drive cosmic evolution, from stellar birth and death to the formation and dissolution of galaxies, operate at every scale of organization. Understanding these patterns can help us find meaning and purpose even in the face of uncertainty and change. If destruction and renewal are fundamental features of complex systems, then the challenges we face as individuals and as a species are not aberrations to be eliminated, but rather normal aspects of existence to be navigated with wisdom and grace. The key insight from the deep time perspective is that meaning and purpose don't require permanence. The trilobites that dominated Paleozoic seas for hundreds of millions of years are now extinct, but their existence was not meaningless. They played crucial roles in the ecosystems of their time, explored unique ways of living and sensing the world, and contributed to the evolutionary history that eventually gave rise to all subsequent life. Their extinction was tragic in its own way, but it also created opportunities for new forms of life to emerge and flourish. Similarly, our own existence as individuals and as a species is temporary in cosmic terms, but that doesn't diminish its significance. We are each unique expressions of the cosmos becoming aware of itself, brief opportunities for the universe to experience beauty, wonder, love, and understanding. The fact that these experiences are temporary makes them more precious, not less. This perspective can transform how we approach both the great challenges and the small pleasures of human existence. Environmental crises become opportunities to demonstrate our capacity for wisdom and cooperation. Personal relationships become chances to create unique forms of connection and understanding. Creative endeavors become ways of adding new beauty and meaning to the cosmic story. Even mundane activities like cooking, gardening, or walking in nature become opportunities to participate consciously in the ongoing evolution of complexity and awareness. The deep time awareness that comes from studying mass extinctions can also provide perspective on personal difficulties and setbacks. The same principles that allow life to recover from catastrophic extinction events operate in human lives as well. Resilience comes from maintaining diversity in our approaches to life, flexibility in our responses to change, and connections to larger communities and purposes that extend beyond immediate concerns. When we face personal catastrophes, relationship endings, career disruptions, health challenges, or other major life changes, we can draw on the same sources of resilience that have allowed life to persist through billions of years of environmental upheaval. These include maintaining diverse sources of meaning and purpose, cultivating adaptable skills and perspectives, and connecting to communities that provide support and opportunities for renewal. The pattern of post-extinction innovation also applies to personal recovery and growth. Often, our greatest breakthroughs and most significant personal developments emerge from periods of difficulty and disruption. Like the evolutionary radiations that followed mass extinctions, personal growth often involves exploring new possibilities that couldn't have been imagined under previous circumstances. This doesn't mean seeking out unnecessary difficulties or viewing personal problems as inherently beneficial. But it does suggest that when challenges do arise, they can become opportunities for developing new capacities and exploring new directions. The key is maintaining the same characteristics that allowed species to survive mass extinctions: flexibility, resilience, and openness to new possibilities. The cosmic perspective provided by deep time awareness can also enhance our appreciation for the present moment. When we truly understand the vast scales of space and time within which our lives unfold, ordinary experiences take on extraordinary significance. The fact that we can experience anything at all, that we can feel the warmth of sunshine or the comfort of companionship or the satisfaction of understanding, becomes miraculous rather than mundane. This enhanced appreciation doesn't require any particular spiritual or religious beliefs, though it's compatible with many different worldviews. It simply emerges from recognizing our place in the larger cosmic story of increasing complexity and organization. We are participants in something vast and magnificent, temporary expressions of the universe's capacity for beauty, creativity, and understanding. As we near the end of our journey through Earth's greatest catastrophes, it's worth considering what practical wisdom we can extract from this deep time perspective. The mass extinctions of the past offer several key insights that can guide both individual choices and collective action in our current environmental crisis. First, they remind us of the importance of maintaining diversity and avoiding over-specialization. Species that survived mass extinctions were typically generalists that could adapt to changing conditions rather than specialists that were perfectly adapted to specific environments. For human societies, this suggests the value of maintaining diverse approaches to technology, governance, and problem solving rather than becoming overly dependent on single solutions. Second, they demonstrate the power of small changes to have large effects over time. Many mass extinctions were triggered by environmental changes that initially seemed relatively minor but cascaded through complex systems to produce catastrophic outcomes. This suggests the importance of paying attention to early warning signs and taking preventive action before problems become unmanageable. Third, they show us that recovery is possible even from the most devastating setbacks, but that it typically requires long timescales and often results in very different communities than those that existed before. This suggests the importance of patience and long-term thinking in addressing environmental challenges, while also recognizing that successful adaptation may require fundamental changes in how we organize our societies and economies. Fourth, they reveal the crucial role of innovation and experimentation in responding to environmental change. The species that not only survived but thrived after mass extinctions were often those that developed genuinely new capabilities and explored new ecological niches. For human societies, this suggests the importance of supporting research, innovation, and experimentation in developing solutions to environmental challenges. Finally, they demonstrate the interconnectedness of all life and the importance of maintaining the complex relationships that bind ecosystems together. Mass extinctions typically began with the breakdown of ecological relationships and cascaded through food webs and other network connections. This suggests the importance of thinking systemically about environmental problems and developing solutions that enhance rather than disrupt ecological connectivity. These insights from deep time can guide our individual choices as well as our collective actions. Understanding our connection to the deep history of life can inspire more sustainable personal practices, from reducing consumption to supporting conservation efforts, to making career choices that contribute to environmental solutions. The cosmic perspective can provide motivation for these choices by helping us see their significance within the larger story of life's persistence and evolution. But perhaps the most important practical wisdom from the deep time perspective is simply the recognition that we are part of something much larger and more magnificent than our immediate concerns might suggest. We are temporary participants in a cosmic story of increasing complexity and awareness, brief expressions of the universe's capacity for beauty and understanding. This recognition can provide both humility about our limitations and inspiration to use our remarkable capabilities as wisely and beautifully as possible. As we continue this gentle exploration of deep time wisdom, We might also consider how the rhythms of extinction and recovery manifest in the smaller cycles of our daily lives. Just as Earth's biosphere undergoes constant renewal through the death and birth of countless organisms, our own bodies and minds are continuously renewed through cellular replacement, memory formation, and the ongoing process of learning and growth. Every 7 years, most of the atoms in your body have been replaced through the normal processes of metabolism and cellular renewal. You are quite literally not the same person you were a decade ago, at least not in terms of physical substance. Yet something persists through this constant material flux, some pattern or organization that maintains continuity of identity and experience across time. This personal experience of persistence through change mirrors the larger patterns we've been exploring tonight. Just as life as a whole persists through the rise and fall of individual species, and just as consciousness persists through the life and death of individual organisms, your sense of self persists through the constant renewal of your physical being. You are a pattern that maintains itself through time, a temporary but meaningful arrangement of matter and energy that has somehow achieved the capacity for self-awareness. In the quiet moments before sleep, when the busy concerns of daily life begin to fade, this deep time awareness can bring a profound sense of peace and perspective. The worries that seemed so urgent during the day take on different proportions when viewed against the backdrop of geological time. The deadlines and conflicts and disappointments that fill our human days become small ripples on the surface of a much deeper ocean of meaning and purpose. This doesn't mean that human concerns are unimportant or that we should become detached from the immediate challenges of our lives. Rather, it means that we can hold these concerns more lightly, with the understanding that they are part of a much larger pattern of change and renewal that has been operating since the beginning of time. Our struggles and achievements, our loves and losses, our hopes and fears, all take place within the context of this vast cosmic story of increasing complexity and awareness. The rhythm of the seasons that we experience each year echoes the much longer rhythms of geological time that we've been exploring tonight. Spring's renewal after winter's dormancy mirrors the evolutionary radiations that followed each mass extinction. Summer's abundance reflects the periods of biological prosperity that characterize stable intervals between catastrophes. Autumn's preparation for winter resembles the gradual environmental changes that often preceded extinction events. Winter's apparent death masks the underground processes of renewal that make spring's resurrection possible. These natural cycles remind us that endings and beginnings are intimately connected, that death and renewal are part of the same fundamental process. The leaves that fall in autumn become the soil that nourishes next year's growth. The dinosaurs that perished in the Cretaceous extinction created the ecological space that allowed mammals to flourish. Even the stars that exploded billions of years ago created the heavy elements that make life possible on Earth. This cyclical understanding of time differs fundamentally from the linear progression that often characterizes human thinking. We tend to view history as a straight line from past to future, or with progress measured by movement away from previous conditions. But the deep time perspective reveals a more complex pattern, where apparent endings become new beginnings, where catastrophes create opportunities, and where the future emerges from the creative transformation of the past. Living with this cyclical awareness can bring a different quality to how we experience both joy and sorrow. Moments of happiness become more precious because we understand their temporary nature, but also more meaningful because we recognize them as expressions of the same cosmic creativity that has been generating beauty and complexity for billions of years. Periods of difficulty become more bearable because we understand them as part of larger cycles of renewal, opportunities for growth and transformation, rather than simply obstacles to be endured. The mass extinctions we've explored tonight also offer insights into the nature of memory and forgetting, preservation and loss. Each extinction event eliminated vast amounts of biological information that had accumulated over millions of years of evolution. Entire ways of being in the world, unique solutions to the challenges of existence, vanished forever when their carriers went extinct. Yet something essential was preserved through each catastrophe, carried forward by the survivors and expressed in new forms during the subsequent recovery. This pattern of selective preservation appears throughout the history of life and consciousness. Not everything can be saved through periods of dramatic change, but the most essential information, the deepest patterns, the core insights, somehow find ways to persist and re-emerge in new contexts. The genetic code that guides cellular function has remained remarkably stable for billions of years, even as the organisms that carry it have changed beyond recognition. The basic neural mechanisms that enable learning and memory have persisted through hundreds of millions of years of vertebrate evolution, even as brains have grown larger and more complex. In human culture, we see similar patterns of preservation and transformation. Languages evolve and sometimes disappear, but the capacity for symbolic communication persists. Specific scientific theories are replaced by better ones, but the accumulated knowledge of how to investigate and understand natural phenomena continues to grow. Artistic styles and cultural practices change dramatically over time, but the human impulse to create beauty and meaning remains constant. Understanding these patterns can help us think more wisely about what we choose to preserve and what we allow to change in our own lives and societies. Not everything from the past needs to be maintained, but we should be thoughtful about which traditions, relationships, and ways of knowing we want to carry forward into the future. Like the survivors of mass extinctions, we need to be both selective and adaptive, preserving what is most essential while remaining open to new possibilities. The deep time perspective also reveals the profound creativity that emerges from the interplay between preservation and innovation. Each mass extinction preserved some elements of the previous biosphere while eliminating others, creating novel combinations of surviving lineages that could explore entirely new evolutionary possibilities. The result was often the emergence of biological communities that were more complex and sophisticated than anything that had existed before. Human creativity follows similar patterns. Our greatest artistic and scientific achievements often emerge from the combination of preserved wisdom with innovative approaches. We build on the insights of previous generations while exploring new ways of understanding and expressing our experience of existence. The music we create today incorporates rhythms and harmonies discovered by countless previous musicians, while exploring sonic territories that have never been mapped before. This creative process is particularly evident in scientific understanding, where each generation builds on the accumulated knowledge of previous researchers while making discoveries that transform our understanding of reality. The story of mass extinctions that we've explored tonight represents just such a synthesis, combining observations made by geologists, paleontologists, climatologists, and many other researchers over several centuries to create a coherent narrative about Earth's biological history. But science is not the only way of understanding and appreciating the deep time story of life on Earth. Poetry, music, visual arts, and contemplative practices can all provide insights into the meaning and significance of our cosmic heritage. The same events we've explored through scientific analysis tonight can also be approached through metaphor, symbol, and direct aesthetic experience. Consider how a poet might approach the Permian extinction, not as a sequence of environmental changes and biological responses, but as a meditation on endings and beginnings, on the transformation of despair into hope, on the way that destruction can clear space for entirely new forms of beauty. A musician might hear in the rhythms of extinction and recovery the deep bass notes that underlie all the melodies of existence, the fundamental oscillations between tension and release that drive both cosmic evolution and human emotion. Visual artists have long been inspired by the forms and patterns revealed by paleontology and geology. The spiral shells of ammonites, the delicate structures of early marine organisms, the massive skeletons of dinosaurs, all provide imagery that speaks to something deep in human aesthetic sensibility. These ancient forms seem to embody principles of beauty and harmony that transcend their biological origins, suggesting deep connections between the processes that create life and those that create art. Contemplative traditions from around the world have also found ways to incorporate deep time awareness into practices that cultivate wisdom and compassion. Buddhist meditation on impermanence, indigenous ceremonies that honour the continuity of life across generations, and modern eco-spirituality movements that celebrate our embeddedness in natural systems all provide frameworks for integrating scientific understanding with spiritual insight. These different approaches to understanding our place in deep time are not competing with each other, but rather exploring different aspects of the same fundamental reality. Science provides precise knowledge about the mechanisms and timescales involved in cosmic evolution. Art provides ways of experiencing and expressing the emotional and aesthetic dimensions of this knowledge. Contemplative practices provide methods for integrating this understanding into daily life and personal development. Together, these approaches can help us develop what might be called deep time wisdom, a way of living that honours both the immediate concerns of human existence and the larger cosmic context within which those concerns unfold. This wisdom doesn't require abandoning human-scale values and attachments, but rather holding them within a broader perspective that can provide both meaning and resilience. Living with deep time wisdom means recognizing that we are both infinitesimally small in cosmic terms and extraordinarily significant as expressions of the universe's capacity for consciousness. It means understanding that our lives are both temporary and eternal, brief in duration but meaningful as contributions to the ongoing evolution of complexity and awareness. It means appreciating both our vulnerability as individuals and our power as participants in a cosmic story that has been unfolding for billions of years. This wisdom can be particularly valuable during times of environmental crisis and uncertainty. When we understand our place in the deep history of life on Earth, current challenges become both more manageable and more significant. More manageable because we understand that life has survived much worse catastrophes and that resilience and adaptation are fundamental characteristics of living systems. More significant because we recognize that our responses to current challenges will influence the trajectory of life and consciousness for millions of years into the future. The mass extinctions of the past thus become not just fascinating topics for scientific study, but sources of practical wisdom for navigating the challenges of our own time. They remind us that catastrophe and renewal are intimately connected, that destruction often clears the way for innovation, and that the capacity for recovery and growth is built into the very fabric of existence. As we prepare to bring our exploration of these ancient catastrophes to a gentle close, we can carry with us the profound lessons they offer about resilience, creativity, and the remarkable persistence of life in the face of seemingly impossible odds. We can draw inspiration from the countless generations of organisms that survived environmental upheavals far more severe than anything our species has yet faced. We can find comfort in the knowledge that the same evolutionary forces that created consciousness in the first place continue to operate today, generating new forms of complexity and beauty, even as old forms pass away. Most importantly, we can recognize ourselves as conscious participants in this ongoing cosmic story, temporary but meaningful expressions of the universe's capacity for self-understanding. Our brief time as aware beings is an opportunity to appreciate, protect, and contribute to the magnificent heritage of life that billions of years of evolution have created. By living with this awareness, we honor both the ancient survivors whose persistence made our existence possible and the future generations whose possibilities depend on the choices we make today. The gentle rhythm of our breathing as we settle into sleep connects us to the atmospheric cycles that have sustained life for billions of years. The warmth of our bodies reflects the same metabolic processes that powered the first cells in ancient seas. The dreams that await us may carry echoes of the same creativity that has driven evolution through countless cycles of extinction and renewal, destruction and rebirth, ending and beginning. In this quiet space between waking and sleeping, between human time and geological time, between individual existence and cosmic story, we can rest in the knowledge that we are part of something infinitely larger than ourselves, participants in a process of cosmic awakening that began with the first stirrings of life billions of years ago and continues through our own brief moment of consciousness and into whatever wonders the future may hold. As we draw toward the end of our journey through Earth's greatest transformations, let's take a moment to gather the threads of understanding we've woven together tonight. We began with the recognition that our planet has experienced 5 great mass extinctions, each representing a fundamental reset of life's trajectory. We've seen how these catastrophic events, terrible as they were for the species that lived through them, also created the evolutionary opportunities that led directly to our own existence. Through the Ordovician Silurian extinction, we witnessed the first great crisis of complex life, a cooling and warming cycle that eliminated 85% of marine species, but also set the stage for life's eventual colonization of land. The late Devonian extinction showed us how success itself can sow the seeds of catastrophe, as the triumph of early forests contributed to environmental changes that devastated marine ecosystems. The great dying of the Permian period brought us face to face with the most severe crisis life has ever endured, when volcanic catastrophes nearly ended the evolutionary experiment altogether. The Triassic-Jurassic extinction reminded us that recovery itself can be interrupted, but also revealed how each setback creates new opportunities for innovation and diversification. Finally, the Cretaceous-Paleogene extinction demonstrated how sudden catastrophic events can redirect the entire course of evolution, eliminating the dominant dinosaurs and creating the ecological space that allowed mammals, and eventually ourselves, to flourish. But our exploration has revealed something even more profound than this sequence of catastrophes and recoveries. We've discovered that mass extinctions are not just geological events, but fundamental processes that reveal the creative nature of cosmic evolution. Each extinction has been followed by innovations that often exceeded the complexity and sophistication of anything that existed before. Jaws, tetrapod limbs, powered flight, echolocation, and eventually consciousness itself all emerged from the evolutionary experimentation that followed mass extinction events. This pattern suggests that destruction and creation are not opposite forces, but rather complementary aspects of a single cosmic process. The universe appears to evolve toward greater complexity and awareness, through cycles that involve both preservation and transformation, continuity and change, ending and beginning. Mass extinctions represent the most dramatic expression of this process on Earth, but similar patterns operate at every scale of organization, from the life cycles of individual organisms to the birth and death of stars and galaxies. Understanding this cosmic context transforms how we think about our own existence and responsibilities. We are not accidental byproducts of meaningless physical processes, but rather the current expression of a universe that has been evolving toward greater complexity and consciousness for billions of years. Our capacity for scientific understanding, artistic creation, moral reasoning, and spiritual reflection represents the cutting edge of cosmic evolution, the universe's latest experiment in self-awareness. This realization brings with it both tremendous privilege and profound responsibility. We are the inheritors of 4 billion years of evolutionary innovation, the recipients of genetic and cultural heritage that spans the entire history of life on Earth. Every breath we take connects us to atmospheric processes that have sustained life for eons. Every thought we think employs neural mechanisms that have been refined through millions of years of vertebrate evolution. Every act of creativity or compassion continues the cosmic process of generating new forms of beauty and meaning. But we're also the first species in Earth's history with the capacity to understand and potentially influence the trajectory of life on a planetary scale. Unlike the victims of previous mass extinctions, we can read the warning signs of environmental crisis and take conscious action to prevent catastrophic outcomes. Unlike any previous generation of humans, we have technologies that could enable sustainable civilization and even the spread of life beyond Earth. Whether we fulfill this potential depends on our ability to integrate the wisdom of deep time with the urgency of immediate challenges. The mass extinctions of the past teach us that environmental systems can reach tipping points where gradual change becomes sudden collapse. They also show us that recovery is possible, but typically requires long timescales and often results in biological communities very different from those that existed before. These insights suggest both caution and hope for our current environmental situation. Caution, because the same non-linear dynamics that triggered past mass extinctions could produce rapid, unpredictable changes in response to current environmental stresses. Hope, because life's remarkable resilience and creativity have enabled recovery from even the most devastating setbacks. The key is acting before critical thresholds are crossed, maintaining the diversity and connectivity that enable adaptive responses, and remaining open to the innovations and transformations that may be necessary for long-term sustainability. This requires thinking like survivors of mass extinction, combining preservation of what is most essential with flexibility and openness to new possibilities. From the personal perspective we've explored tonight, this deep time awareness can bring both humility and empowerment. Humility because it reveals how temporary and contingent our individual existence is in cosmic terms. We are brief patterns in the vast flow of matter and energy, temporary arrangements of atoms that briefly achieve consciousness before returning to the cosmic recycling process. Our worries and achievements, our loves and losses, our hopes and fears, all unfold within the context of changes so vast and slow that they dwarf human comprehension. But this same perspective can also be profoundly empowering, because it reveals that we are not separate from cosmic processes, but rather their most sophisticated expression. Through us, the universe has developed the capacity to understand its own history and contemplate its own future. Our consciousness represents 4 billion years of evolutionary problem solving, the accumulated wisdom of countless generations of organisms that survived whatever challenges their environments could produce. This means that when we think clearly, we are the cosmos thinking about itself. When we create beauty, we are the universe expressing its aesthetic potential. When we act with compassion, we are cosmic evolution manifesting its tendency toward greater complexity and cooperation. When we work to protect and preserve life, we are participating in the same fundamental processes that have enabled life to persist through every catastrophe our planet has produced. Living with this awareness doesn't require any particular spiritual or religious beliefs, though it's compatible with many different worldviews. It simply emerges from taking seriously what science has revealed about our origins and our place in the cosmic story. We are literally made of star stuff, as the astronomer Carl Sagan famously observed, but we are star stuff that has organized itself in such a way as to contemplate the stars. This scientific understanding can inspire the same sense of wonder and reverence that has traditionally been associated with spiritual experience. The fact that unconscious matter has somehow given rise to consciousness, that random mutations and environmental pressures have produced beings capable of love and creativity and moral reasoning, that a universe that began as a simple expansion of space and time has evolved into galaxies and planets and ecosystems and eventually into minds capable of understanding this entire process. All of this seems miraculous regardless of the mechanisms involved. The mass extinctions we've explored tonight are part of this larger miracle of cosmic evolution. Without the Ordovician extinction, life might never have colonized land. Without the Permian extinction, dinosaurs and mammals might never have evolved. Without the Cretaceous extinction, human consciousness might never have emerged. Each catastrophe eliminated some possibilities while creating others, channeling the creative power of evolution in directions that would have been impossible under previous conditions. This doesn't mean that mass extinctions are good things or that we should welcome environmental catastrophe. The losses involved in each extinction event were real and irreversible, representing the permanent elimination of unique forms of beauty and complexity. But it does suggest that even the most devastating setbacks can become opportunities for breakthrough innovations, that destruction and creation are intimately connected in the cosmic process of evolution. For our current environmental challenges, this perspective suggests both urgency and patience. Urgency because the window for preventing the worst outcomes may be closing rapidly. Patience because the solutions we develop may require fundamental changes in how human societies organize themselves and relate to natural systems. The transition to sustainability may prove as significant as the transition from single-celled to multicellular life, or from aquatic to terrestrial existence, or from unconscious matter to conscious awareness. Such transitions don't happen overnight, but they do happen. The history of life on Earth is a history of seemingly impossible transformations that somehow occurred through the patient accumulation of small changes and the creative response to environmental challenges. If we can learn to think and act on the timescales that characterize these great transitions, we may be able to navigate our current challenges successfully. But even if we can't, even if human civilization proves unable to achieve long-term sustainability, the deep time perspective reminds us that the story will continue. Life survived the asteroid impact that ended the Cretaceous, and it would survive whatever catastrophes human activities might produce. The evolutionary creativity that has generated 4 billion years of increasing complexity and diversity would continue to operate, exploring new possibilities and generating new forms of beauty and meaning. This doesn't diminish our responsibility to act wisely in the present, but it does provide perspective that can help us act with both urgency and equanimity. We are participating in something much larger than our immediate concerns, contributing to a cosmic story that began long before us and will continue long after us. Our brief time as conscious beings is an opportunity to appreciate and protect the magnificent heritage we've inherited, while also contributing whatever we can to its continued evolution. The great mass extinctions of Earth's past thus become sources not just of scientific knowledge, but of wisdom for living. They remind us that change is the fundamental character of existence, that destruction and creation are intimately connected, that resilience comes from diversity and adaptability, and that even the most catastrophic setbacks can become opportunities for breakthrough innovations. They also remind us that we are part of a much larger story, participants in a cosmic process of evolution toward greater complexity and consciousness. This story includes both the terrible losses represented by each extinction event and the remarkable recoveries and innovations that followed. It encompasses both the vulnerability of individual species and ecosystems and the extraordinary resilience of life as a whole. As we settle into the quiet space at the end of our exploration, we can carry with us this dual awareness of fragility and resilience, loss and renewal, ending and beginning. We are temporary patterns in the vast flow of cosmic evolution, brief opportunities for the universe to experience itself consciously, but we are also expressions of the same creative forces that have been operating since the beginning of time, participants in an ongoing process of generating new forms of complexity and beauty. The mass extinctions we've explored tonight are chapters in this larger story, reminders that the universe evolves through cycles that involve both preservation and transformation. They show us that consciousness itself emerged from the creative response to environmental challenges, and our capacity for understanding and appreciation represents the culmination of billions of years of evolutionary innovation. Most importantly, they remind us that we are not observers of natural processes, but participants in them. Our thoughts and actions are part of the ongoing evolution of complexity and consciousness on Earth. By living with awareness of our place in this cosmic story, by making choices that honor both our immediate needs and our long-term responsibilities, by contributing whatever we can to the protection and flourishing of life, we participate consciously in the same fundamental processes that have enabled existence to become ever more complex and beautiful and aware. In these final moments of our exploration together, let's rest in the profound recognition that consciousness itself represents the universe becoming aware of its own magnificent history. Through our capacity to understand the deep time story of mass extinctions and recoveries, we embody the cosmos reflecting on its own journey from simple beginnings to extraordinary complexity. Every insight we've shared tonight, every moment of wonder at the resilience of life, every recognition of our own improbable existence, represents the universe contemplating itself through the temporary arrangement of matter and energy that we call human consciousness. the trilobites that scuttled across Ordovician seafloors, the early tetrapods that first ventured onto Devonian shores, the massive dinosaurs that ruled Mesozoic landscapes, the small mammals that survived the Cretaceous catastrophe, all were expressions of the same creative force that now manifests as our ability to read their stories in stone and to appreciate their role in the vast narrative that led to our own existence. We are their legacy, their gift to the future, the culmination of billions of years of survival against impossible odds. This perspective transforms even our smallest daily experiences into expressions of cosmic significance. The morning coffee that warms your hands connects you to plants that photosynthesize using mechanisms perfected over billions of years. The conversation you have with a friend employs language capabilities that represent millions of years of neural evolution. The music that moves you resonates with auditory processing systems, refined through countless generations of vertebrate ancestors. The beauty you perceive in a sunset activates visual pathways that have been shaped by hundreds of millions of years of natural selection. We carry within our bodies and minds the accumulated wisdom of every organism that contributed to our evolutionary lineage, the capacity to extract energy from food, to repair cellular damage, to fight off infections, to learn from experience, to form emotional bonds, to create and appreciate beauty. All of these represent solutions to fundamental challenges of existence that were discovered through the long process of evolutionary experimentation and refinement. Yet, we are more than just the sum of our evolutionary inheritance. Consciousness has brought something genuinely new into the universe, the capacity for reflection, choice, and intentional action, guided by understanding rather than just instinct. We can contemplate alternative futures and work toward those we prefer. We can learn from the mistakes of the past and try to avoid repeating them. We can even sacrifice immediate benefits for long-term advantages, something that requires a kind of temporal awareness that appears to be unique to conscious beings. This capacity for conscious choice places us at a remarkable juncture in Earth's history. For the first time, a species has emerged that can understand the processes that shaped its own evolution and potentially influence the future course of that evolution. We can read the story of mass extinctions in the fossil record and use that knowledge to avoid triggering another one. We can understand the requirements for ecosystem health and work to maintain the conditions that support biodiversity. We can even imagine spreading life beyond Earth and taking the first steps toward making that vision reality. Whether we fulfill this potential depends on our ability to integrate rational understanding with emotional wisdom, scientific knowledge with ethical insight, individual needs with collective responsibilities. The same cognitive abilities that allow us to understand complex systems also make us capable of impressive self-deception and short-term thinking. The same technologies that could enable sustainable civilization could also trigger environmental or social catastrophes if used unwisely. The deep time perspective offers guidance for navigating these challenges by revealing the long-term consequences of different choices and the fundamental principles that have enabled life to persist through previous crises. Diversity provides resilience. Flexibility enables adaptation. Cooperation creates opportunities for mutual benefit. Innovation opens new possibilities when old approaches become inadequate. These principles, discovered through billions of years of evolutionary trial and error, remain as relevant today as they were during ancient extinction events. But perhaps the most important insight from our journey through deep time is the recognition that meaning and purpose don't require permanence or certainty. The organisms that lived and died during Earth's great catastrophes weren't failures because they didn't survive. They were successful expressions of life's creativity during their time, contributors to the ongoing experiment in complexity and consciousness that eventually gave rise to our own existence. Their lives had meaning not because they lasted forever, but because they participated fully in the cosmic process of evolution and development. Similarly, our own lives have meaning not because we will exist forever, but because we represent the current frontier of cosmic evolution, the universe's latest experiment in self-awareness and conscious choice. We are temporary but magnificent expressions of billions of years of creative development, brief opportunities for existence to experience itself subjectively and to contribute consciously to its own continued evolution. This recognition can free us from the anxiety that comes from demanding permanent solutions to temporary problems. Instead of seeking to eliminate uncertainty and change, we can learn to dance with them, to find meaning and purpose in our responses to whatever challenges arise. Instead of demanding that our individual lives be cosmically significant, we can find significance in being conscious participants in a cosmic process that is inherently meaningful. The mass extinctions we've explored tonight remind us that change is not the enemy of meaning, but rather its foundation. Without the environmental changes that triggered past extinctions, the evolutionary innovations that followed would never have occurred. Without death, there would be no birth. Without endings, there would be no beginnings. Without the creative destruction that characterizes complex systems, there would be no ongoing development of complexity and beauty. Living with deep time awareness means embracing this creative aspect of change while working skillfully to influence its direction. We can't prevent all environmental disruption or eliminate all sources of uncertainty, but we can work to ensure that whatever changes do occur serve the continued evolution of life and consciousness, rather than their destruction. We can act as conscious agents of the same evolutionary creativity that has been operating since the beginning of time. In our relationships with other people, this might mean supporting their growth and development rather than trying to keep them exactly as they are. In our relationship with the natural world, it might mean working to enhance ecosystem health and resilience rather than trying to preserve unchanging wilderness. In our relationship with technology and culture, it might mean promoting innovations that serve long-term flourishing rather than just short-term convenience. Most fundamentally, living with deep time awareness means recognizing that we are not separate from the natural world, but rather its most sophisticated expression. We are nature becoming conscious of itself, evolution developing the capacity for self-direction, the cosmos awakening to its own beauty and potential. This recognition brings with it both the humility that comes from understanding our place in something much larger than ourselves, and the empowerment that comes from realizing that we are active participants in the ongoing creation of reality. As our exploration draws to its gentle close, we can rest in the profound peace that comes from understanding our place in this vast cosmic story. We began tonight by contemplating catastrophes so severe they eliminated most life on Earth, events that might seem to suggest the meaninglessness or fragility of existence. But we've discovered instead that these catastrophes were essential chapters in a larger story of resilience, creativity, and the gradual development of ever greater complexity and consciousness. The same processes that have enabled life to survive and thrive through 5 major mass extinctions continue to operate today. The creativity that has produced 4 billion years of evolutionary innovation continues to generate new possibilities. The resilience that has carried life through every conceivable catastrophe remains available to us as we face our own challenges and uncertainties. We are the inheritors of this magnificent legacy, temporary custodians of the most complex and beautiful phenomenon we know of in the universe, conscious life itself. We carry within our minds the capacity to understand our own origins and to influence our own future. We embody the universe's capacity for self-reflection and conscious choice. Tonight, as you settle into sleep, you can rest in the knowledge that you're part of something infinitely larger and more beautiful than any individual existence, yet also uniquely valuable as your own particular expression of cosmic consciousness. The dreams that come may carry echoes of the same creativity that has driven 4 billion years of evolution, the same resilience that has carried life through every catastrophe our planet could produce, the same wonder that has enabled existence to become aware of its own magnificent complexity. The atoms that compose your sleeping body will continue their ancient dance, the same dance they've been performing since the first stars forged them in nuclear fires billions of years ago. The patterns of neural activity that create your dreams will employ mechanisms refined through hundreds of millions of years of vertebrate evolution. Even in sleep, you remain a conscious participant in the ongoing story of cosmic development, a temporary but meaningful expression of the universe's journey toward ever greater beauty and awareness. And tomorrow, when you wake, you'll carry with you the deep time perspective we've shared tonight, the recognition that you're both infinitesimally small in cosmic terms and profoundly significant as an expression of cosmic consciousness. You'll understand that your life, however brief, is part of a story that stretches from the first stirrings of life in ancient seas to whatever magnificent possibilities await in the far future. The mass extinctions of Earth's past become not just fascinating chapters in natural history, but sources of wisdom for living consciously in the present. They remind us that resilience comes from diversity and flexibility, that innovation emerges from creative responses to challenge, that meaning arises not from permanence but from conscious participation in the ongoing evolution of complexity and beauty. Where are you listening from tonight, and what time is it there? I always find it wonderfully moving that we're connected across space and time by our shared curiosity about these ancient mysteries, united by our wonder at the remarkable story of life on Earth. If this gentle exploration of our planet's greatest catastrophes has helped you relax or sparked some quiet curiosity about our cosmic heritage, perhaps you'll consider supporting this channel with a like or subscription, helping us continue to explore the magnificent intersection of science and serenity. Sweet dreams, fellow travelers through deep time. May your rest be peaceful, your dreams filled with the quiet wonder of existing at all in this vast and beautiful cosmos. And may you wake tomorrow with a deeper appreciation for the extraordinary privilege of consciousness, the remarkable resilience of life, and your own meaningful place in the continuing story of cosmic evolution. Remember, tonight's exploration was intended for relaxation and gentle education rather than comprehensive scientific instruction, but the wonder it reveals is absolutely real. You're made of star stuff that has organized itself to contemplate the stars, a temporary arrangement of ancient atoms that has somehow achieved the capacity for love, creativity, and understanding. That's not just beautiful poetry, it's the most profound truth that science has revealed about our place in the cosmos. Rest well in that knowledge, and may your dreams carry you gently through the quiet hours until morning brings new opportunities to participate consciously in the magnificent, ongoing story of existence becoming ever more complex, beautiful, and aware.